Yes, sir. Now it's visible.
Now it is visible.
The presentation is yes.
Oh, what is coming here? I don't know. Coming here. Just wait.
Origin file is open.
Sorry. I probably opened the wrong file. Mm-hmm. This okay?
Yes, sir.
Yeah.
So you can just open the presentation mode. Yes, sir.
Probably it's okay now. Right? I hit this button. Yeah. So thank you so much. Really, I thank Professor Shoibal Mukherjee for the invitation, and unfortunately, I'm very sorry that I could not come personally. So,
Sorry to interrupt. So you can just switch on the presentation mode.
Is it right?
And minimize the screen. Yes, sir. Minimize the Google Meet screen.
Minimize the Google main screen is.
You can drag it downwards.
Okay. Is it okay?
Yes, sir. It's perfectly fine.
Okay, that's fine. So, yeah, thanks for for inviting me. So, this is the title of my talk. I modified it a little bit based on the so-called medium. I'll be talking of photonic and energy harvesting devices. Okay, so I start with a kind of textbook lecture. I don't want to give in introduction over. So as you know, the semiconductor devices are aggressively scaled. So this is a typical block diagram of a CMOS device. Contains an NMOS and one PMOS. And the switching time of the devices are controlled by the capacitance and the current. So basically it is equivalent to basically L square by mu, where mu is the mobility and L is the channel length. So since if the L is reduced significantly, the switching time will be reduced faster. So that's why when we scale the device length by a factor of 2, we have got lots of advantages. We gain a lot. Density increases by k square. Speed increases by k. On the other hand, power dissipation comes by a factor of 1 by k square. And the main figure of merit is the power delay 1 by k cube. As you see, all of these lots of advantages. We get high speed computer, we get a low power computer, we get high density circuits or a memory circuit. Now the question is that where are you now? We are in the age of beyond Moore era. So as you know, Moore's law actually has predicted us that we can go up maybe about 8 nanometer in terms of wavelength. After that, the Moore's law is not. But if you see that the devices that we have, they are already crossed that limit. And today, in a state-of-the-art devices, you can have up to 1 billion transistors, 100 billion transistors per chip over a computer. And if you see the next 5 years, it is expected to be more than about 200 billion transistors. So this is monolithic integration. Dimensional heterogeneous integration, which all the AI companies like NVIDIA wants, can have easily about 1 trillion transistors. Now this comes with a lot of problems. It's called power. Power distribution is enormous. Question is that if the devices are not low power, power distribution will be extremely high, and that is our big problem. So just I want to have an estimate that device scaling in the range of 5. I have taken only about 30 billion transistors per chip with a 9 nanometer node. And each of the devices work with a switching energy of 130 octojoule. See, auto is a very small number, 10 to the minus 8 joule each transistor. And suppose it starts with a clock speed of 10 gigahertz. You can see that the power distribution in the semiconductor chip is in the range of 260 kilowatts, which is enormously high. So the question is that can we really go down to 1 nanometer or 2 nanometer node? Then what will be the power distribution in the chip? And if the temperature goes up, what will be the power? So that is actually the issue that is happening right now in the device scaling. And as you know, very parallelly, there's one more going up very, very fast is that artificial intelligence. And this is backed by the semiconductor devices application. So now AI is everywhere, online. So that is the language processing, self-driving vehicle, security application, IoT application, all that. But you see, there is a kind of a side effect. There is a problem of the AI also. These data centers are taking huge amount of power and a very, very large carbon dioxide footprint. So already people are scared about that. What will happen to the AI if we have a scarcity of the power, scarcity of the water? So you see, this is a new act I'm saying that AI should need as much as the electricity as the entire country. Okay, so basically what you need to do is you need to develop efficient hardware solutions. If the AI can sustain, continuous development of progress. Just for comparison, in 2011, that's called IBM Jeopardy computer, which was some kind of AI model, was taking on about 200 kilowatt power. And you see that 2016, it takes about 100 CPUs and 166 power consumption was in the range of 300 kilowatt. And even 3 years back, ChatGPT was taking about 60 megawatt of power. Today, AI actually servers take range more than about 100 megawatt, 200 megawatt. So that will be very big power. On the other hand, the device engineers, electronics physicists are trying to do how the brain works. The brain has got so many power, and you see the brain has got about 6 per centimeter square, 6 synapses per centimeter square, and we can take lots of our brain, but brain takes only about 20 watt of energy. So the question is that whether we can have a computing based on the brain mimicking or brain mimicking. So based on that, my lecture theme is that basically we try for some low power devices and circuits. So there can be many things, but in my group we are working on this three areas. We are working in photonic integrated circuits. We are using 2D, 3D integrated structures. We are also working on informatic devices. Unfortunately, due to the lack of the time, I will not cover this part. Rather, I will cover how to generate more efficient energy so that we can back these devices using non-conventional energy sources as electrical power. So that means basically the area of photovoltaics. So I will probably discuss that. Okay, so my first topic is the integrated photonic device. And as you know, this integrated photonic devices have to be silicon compatible. Silicon CMOS like this, because your memory, logics are all silicon CMOS. So switching has to be also by that photonic devices. You need lasers, you need detectors, you need operators. But unfortunately, as you know, the silicon, germanium, they are integrated band capsule conductors. They cannot give light output. They don't give lasers or LED. So the question is that how can you solve the problem? The problem is complete hybrid. Some 3-5 lasers are actually integrated on silicon. That is a very good technology. It's not very efficient, very complicated. So because of that, we are trying for some new materials and give rise to light emission from band gap materials. Okay, so our first thing was that we have to make detectors. So here in this talk, I'll be discussing more on the detectors, not the emitters. So see, as you know, this is the different regions of the electromagnetic spectrum. As you know, in this right side of this presentation file. So one important area is, or one important is radiations. For all telecommunication wavelength range of 1.5 micrometer, this is the near infrared wavelength. Devices that this wavelength. In addition, that you see that lots of other examples are there for many other wavelengths. Okay, but right now we'll stick to this 1.54 micrometer wavelength. So how do we make these devices? which is silicon compatible or silicon compatible. We start with a silicon substrate. Rather, we start with the silicon substrate, which is called SY. And on that, first, grow some germanium quantum. So how the germanium quantum? Because germanium is lattice about 4.2%. So if you grow with a reactional germanium on silicon, initially there will be few layers grown as a layer growth. Then there will be a lot of strain will be developed, and it will give rise to some elastic strain, which is known as the Stansky curve. So this schematically, to grow at low temperature, high vacuum, you can make germanium nanocluster like this. That's why you see in the right side the AFM figure. The growth has been done by the MBE technique that have we have got the MBE that the science lab, and this is a typical growth condition. You see growth condition very temperature is quite low, only 500 degrees centigrade. And an average height of this nanocluster is 12 nanometer, diameter is about typically 50 to 70 nanometer. So now by using electron microscopy and photolithography, you started processing devices. I'll not go to the direct stage. After developing, you can silicon nanowire lithography actually decorated with lot of germanium quantum. So we use one of these silicon nanowire, germanium quantum decorated silicon nanowire to make phototransistor devices. So this is the transfer IDV characteristics of the transistors. And as you see, the dark current changes. Dark current is very low in the range of 20. So because this is a fully depleted SY channel, the quality is extremely good, and you get a high on-off ratio. And as we in with lights of different wavelengths, but starting from 1400 to 1600 nanometer, our interest is around 1500 nanometer. We get a lot of actually photocurrent. So the peak photocurrent we get at 1500 nanometer, which is very close to our optical fiber propagations. Then we try to find out the response. Which is one of the important figure of that. So at a bias of -4 volts, we can get about 5.5 ampere per watt. So if you compare with the commercial silicon detector, commercial silicon detector has responsibility of 0.5 ampere per watt. So this is an order of magnitude higher. So this has been possible due to reduced combinations in low dimension nanoaspect. Now, if you want to really improve better and better devices other materials, like in this case, we have gone to another material called material or tin-based alloy, like a germanium alloy. Now, this is very interesting. About 8% of tin, germanium is indirect band gap, indirect band gap. But theoretically, it has been shown that if you can go to 10 to 12% of tin, you can get a direct band gap semiconductor. But unfortunately, it is very difficult to have a tin germanium alloy because of the extremely low solubility of germanium. This is due to the thermodynamic problem. It has very high lattice space. But anyway, what we could do tin germanium nanowire, as you see, these are 4-shelled tin germanium nanowire. So you have got tin in the core and germanium in the cell. Tin germanium in the core and germanium in the cell. Easily grow it. And tin percentage was about 8%. So this was done with a group in Canada, demonstrating. And then by electron beam we again make a single nanowire in germanium. This is the so-called the ACM protocol here. And this characteristic is now much better than a pure germanium quantum dot. So you just come to this curve like responsibility as a voltage. Remember the earlier we have got a watt and -4 volt. Now we can get a more than about 60 ampere watt about -4 volt, 1 volt. So huge advantage of the absorption and a high responsibility and high gain. This has been possible because the tin germanium is now almost like quasi-direct semiconductor. The absorption coefficient is much higher compared to germanium. Now, since we are already reaching the having the device length scale in silicon-based devices, there are a lot of alternative materials are coming into picture. For the last decade, one material is very, very important for the two-dimensional materials. And this two-dimensional material from transition metal dipole are very important for photonics applications. Ideally, you can make source with that. And depending upon the material, you can have something in the near infrared to ultraviolet, a lot of transition metal dipole kernel, to WS2, tin sulfide, tin cyanide, all in the wavelength. So this is a very good material system for photonic devices. If you see most of the work actually started from after 2010, more than 1 decade, when somebody found out one deep band gap in MOSFET. Lot of work is going on about detector, hand-out structures. And now we are entering into the photonic devices using materials. So this field is going with a speed. We have also worked on this material and also material for making a high efficiency device. I'll just show a few examples. Our first work started about 7-8 years back. When Shubhajit was there, we didn't have any growth or transfer techniques. We simply made that MOS to nanocrystal by liquid phase exfoliation. And we can make different sizes of the nanocrystal by changing the centrifugation speed and actually chemical explosion techniques. And this was really very device quality materials. As you can see that we could see detection. I can show you the emission. They are great band gap material so that they can emit at good temperature, visible wavelength. But I can see that their temperature was quite hot. So this way we don't take a response. And ideally, it's very, very white light LED. As you see, the light is coming out. This is captured in a mobile phone. Simply, you can have a bluish white light. Similarly, if you actually make hybrid structures with other materials like lead sulfide, you easily get a kind of a two-band. MOS2 gives the protection in the range of visible wavelength, like about 500 to about 900 nanometer. The lead sulfide is infrared. You can tune the infrared wavelength and you can see from 1200 nanometer to 1500 nanometer by varying the size of the lead. So this shows this hybrid material is extremely for making futuristic photonic devices. One more 2D material I will discuss, which is anisotropic. Either black phosphorus or black arsenic. So the one on the right is basically the anisotropic structure. Actually, this has got very, very low band gap, black arsenic. It's a good for ion detection, and this is puckered honeycomb structures. So basically, as you can see, you have got both here and structure. So this gives rise to some kind of in-plane and out-of-plane anisotrope. That is extremely useful for making devices. So use this black arsenic or germanium, for example, by physical exfoliations. So as I show, this is the right side, black arsenic or germanium. Germanium GOI wafer, germanium and again we made a very good photographic method. As you see, they are sensitive not only to 300 nanometer, you can go up to about 4 micrometers. So you can go up to the near infrared to infrared. Okay, so basically that we get a quite moderate power level of a photo to dark current ratio of 500 and get a test response at a 3 micron wavelength for many applications. Now I'll switch gear and we'll come to another material. This is coming very fast. So till now I was talking about low power devices. But since the power consumption is going high, we can really generate power with high efficiency. That is also equivalent to the power saving. And that should be non-conventional energy source, the coal or the fossil fuel. So this is a basically now, see, one material has coming up very fast. It is called perovskite materials. So you see perovskite materials. Sorry, this is a very good word. So perovskite materials that made by the Chinese company Longing has already achieved up to 34% efficiency of perovskite from silicon. So, of course, it's much better than single crystal silicon technology. But of course, 3-5 semiconductor shows more efficiency, but they are very efficient. Okay, so what is this perovskites? Perovskites are material, it's like ABA structure. Well, you have got A side is taken by monomer, methyl ammonium FA. B side is taken by divalent cation like lead, etc. And X side is basically anion side is basically halide anion. They can actually exist in different kinds of crystal structures. So this can be cubic, tetragonal, orthorhombic, as well as phase. And this is a big problem. There is always during the processing, there is a transition from cubic to orthorhombic to delta phase of the non-phase. So this is a big problem. So different kind of perovskites can be used. We have used all inorganic perovskites without any organic materials in this. And our aim is to find out that whether we can make some projector glasses, solar cell at room temperature and laboratory ambient conditions without using any glass box. So this perovskite has exceptional equivalent. They've got high absorption coefficient and the first material that we use lead iodide with a beta phase. I told you there are many phases. So beta phase can be actually the beta phase in the sodium lead iodide nanowire. And as you see, this is all in room temperature, atmosphere. The solution is stable up to 30 days in normal ambient without a glass box. And you see that after we put the film, we could see up to 175 degrees centigrade after 15 days, just completely stable. This beta phase cesium lead iodide. So we use this material to make a solar test using a planar heterojunction technology. So where either I use beta phase cesium lead iodide or gamma phase, C60 and BCP as the ETL layer. Okay. And P dot PS is actually full transport layer. And as you see that immediately we got the solar cell efficiency was not that high, but the enhancement was from 4% to about 7% when you go from the gamma phase to the beta phase. So almost 150%, actually the 50% enhancement as you go to the beta phase. So this was published about 5 years back. Once we have found out that stability, this alpha phase cesium lead iodide is a beta stable. And most of our work afterwards are actually based on the alpha phase cesium lead iodide. They are extremely stable. They show a very strong photoluminescence and actually you are working the last 5 years. Okay, lots of students are working and publishing papers. So maybe I'll show one or two results from that. As I said, that alpha phase cesium lead iodide is completely done as a PSS on ITO. Okay, this we call the inverted solar cells configurations, where the P dot PS is the whole transport layer. On the other hand, BCP is the transport layer, and this is cesium lead iodide. And it's compatible to completely flexible devices. And as you see that we engineered this P dot PSS with some DMS. And ultimately found that 5% of DMS additions gives a high open circuit voltage and a high short circuit current. So as you see, this was reported by us in 2020 to advanced functional materials. Efficiency that time we got about 11%, whereas the record-breaking efficiency was 11.4%. But please remember, our devices were not passivated, neither in glove box, was done on all ambient conditions. So that was a tremendous progress on this. And we also see, why did you do cesium lead iodide? Because cesium lead iodide has a band gap, which is of the solar spectrum, about 1.5 electron volt. On the other hand, cesium lead is more stable, but its band gap is actually much higher, about 2.5 volt. So we use this perovskite cesium, the 2D nanocrystals, as a sensitizer. So instead of light sensitized solar cells, we put the nanocrystal sensitized solar cells. Otherwise, the device structure is exactly the same that way you use, and you see your device efficiency was actually much more for the cesium lead iodide compared to cesium lead bromide. So 1.5% compared to about 2% in case of cesium lead bromide. That clearly shows that cesium lead iodide is the real material for photovoltaic devices. But unfortunately, it is extremely unstable. That's problem we are taking care. Now, the question is that, can we make heterostructures using 2D materials and this nanocrystal? The answer is yes. You can make mixed dimensional heterostructures using these two materials like 0D on 2D, 2D on 2D, 2D on 3D. Okay. So in this particular case, we use the 2D, 0D heterostructures. Perovskite nanocrystals are actually that zero-dimensional structures, and the 2D layer is a transport layer. I'm trying to see that whether we can really make a very high quality devices. Okay, so this is the device structure on the right side. As you can see that nanocrystals coated and 2D material here we use a WS2. WS2 is a mechanically exfoliated single monolayer structures. As you see here, actually photograph, and the electron beam discreptography pattern this structure and make this heterostructure. So since this cesium lead iodide nanocrystals are strong light absorber, actually you see in the transient photoluminescence, time resolved photoluminescence, and create lots of electron hole pairs and all are connected, all these are actually transported to WS2. Yes, as a WS2 transport layer. That's why you have got a very, very fast PF. And then if you fabricate the devices, you can just a 3-terminal device structure, and this is a transistors. Okay, WS2 material, chromium and gold as the electrolyte, and of course it is decoated by cesium lead iodide nanocrystals. So the excellent output characteristics, and you see that compared to dark, we have got a very, very high output to dark ratio about 10%. It is unthinkable in a solution process material like cesium lead iodide, and WS2 is also new material. So we get a very, very good interface, high peak to current, output dark current ratio, and the noise current is also extremely in the range of picoampere. Okay, then actually we measure the response of the photodetectors. So I will just show you one of the stuff, the responsibility and the use of power. You remember in the germanium case, we have got about 5 ampere per watt, 6 ampere per watt. But you see, in this case, we are getting about 10 to 4 ampere per watt. So, because this perovskite nanocrystal, there's more absorber, and WS2 is a very nice channel material. So, the gain is extremely high. You get a detectivity about very high detectivity different devices. Operating voltage high, operating voltage dioxide thickness was about quite high, 300 nanometer. So we can use this device in different vias, either the accumulation or depletion. So a detector, the quality of a detector depends upon whether it is a good detectivity. So when at a high positive voltage, you see in the acquisition region you get a high photoresponsitivity, but in the depletion region you get a high sensitivity or low noise thickness. So depending upon your requirement, you can use different bind voltage and find out where do you use. And this is not the very recent work that we see that we can make LED using this. We can nanocrystal also. And actually, we have lots of media news on our new material. This is actually, this is a particular fault. This is called planar defects for Donaldson proportional fault. So we engineered these RP faults by using some ligand. I am not going to the details. This is basically the diffraction pattern where it shows that actually there are lots of planar faults or the RP faults. So we engineered them with a so-called and once we passivate with the ligand, we get a very, very good quality LED devices. Okay. The first one in the information is precision bromide. Some kind of iodine ligand, you see bromide iodide. Wavelength change from actually that you see the green to your red. Not only that your power requirement or threshold power density is extremely low compared to generated bromide. So this was published in last year in Advanced Materials. So I think I have got another 3-4 minutes. I'll take the last topic and finish it. Maybe 2-3 minutes. I'll not take 5 minutes. So we know that you can make solar cells, you can make some other devices for generating energy. But there are also much easier way to generate energy by a process called mechanical energy harvesting. This energy is always lost. This can be done either by using nanojet materials or a trioelectric materials. Think of in the weekends some of the multinational some cities like Indore, Kolkata, or Bombay, lot of people are dancing in the dancing floor. The question is that can you use trioelectric pads or trioelectric mats to get the energy generated from the dancing floor? Trioelectricity is very, very well known. Is this depends on the electrostatics or static electricity. As you know that from our childhood, if we come over here in the winter, we can easily create some charges or the electrostatic charges called tribo charges, and you can just basically paper in also tribo material. You can have some kind of a attraction from that. So basically, I don't want to go to the mechanics. What we are trying to see in our lab is we are able to trioelectric materials we can use for medical electronics or power generations. So we used something called the silk is abundantly available in India that I can embed in a waste material and use a so-called neutral framework network. And from there, actually, we are trying to basically generate trioelectric power. As you see, the voltage output in this is some AC voltage, and AC voltage to voltage is about 389 volts, and it gives rise to power about. The density is not very high. The current in this tribo device is very, very small, but still these are waste energy. These are otherwise getting lost. So this trioelectric material is good to basically charge a capacitor or basically lighting a blue LED in this power. 220 blue LED is simple by actually. So let me check whether this video works. You can see this video works by simple hand tapping. You can have 200 blue LEDs. You can generate tribo power. So otherwise. So that means that this is maybe efficient way to generate some energy, so-called the mechanical energy harvesting. And we use that to basically make a sensor which has been patented now. So basically, as you know, in our today's modern life, many of the patients are at home alone. So you just put a trioelectric patch here. Because the patient has got due to some accident, he falls down. So from the cloud, you will get immediately signal that there is a problem, emergency for the patient, and you can run back home and take care of the patient. This can be useful for very medical applications. But till now, you have seen only tribomaterial with a acidic voltage. But actually, you know that DC is the one thing that you want for many applications. So normally, you can use, of course, the AC and you can use the rectifier in DC. But changing the device structure in this case, using a TMDC silicon-based heterojunction devices, make direct current UV sensitive dielectric nanogenerator, which can be used as a UV sensor or a visible image sensor as well as triboelectric nanogenerator. Which published in Advanced Functional Materials. In this case, it is shown that as you see that this is the response of the material was of course is here that we have used. Not doing that. Basically, it was a silicon and WS2 based options. And in the UV light, it gives a very high QC and ISC. So you can generate a lot of power and it also behaves as a very good sensor. So that is actually we get tribe outputs with increasing illumination power of the UV. So that is one kind of a application of the nanogenerator. So I think I'll conclude now. Conclusion, we want to say that I just don't want to say point-wise. I want to say my this thing that nowadays future devices will be all hybrid devices, silicon, 2D materials, perovskites, and many other materials. So you are already, as you see, scaling of silicon is almost in 2025 or 26, almost saturating. So you have to bring heterogeneous scaling like 2D materials on silicon, or maybe perovskites on silicon, or a new materials on silicon to make a high performance device. So one of the ways is a 2D hybrid materials, heterostructures, or perovskites for. So thank you so much. This is my appointment. I'm my students. Some collaborators like Lee and Mount Abbey from Montreal, and the funding agencies who has actually funded my projects over the years. So thank you very much for your attention. So I'll be very happy to take part.
Thank you, sir, for such an interesting talk. Sir, we are running short of time, so we'll take only one question.
Sure.
Any question from the attendees and participants?
Sir, interesting talk as always. One question is like 2D geometry, sir, many different materials are also being invented. So what is the future of 2D materials, you think, in the domain of semiconductor manufacturing and devices for applications?
So I think that one of the main applications, the main application of 2D will come on, as you know, that silicon thickness has to be very, very low. Body thickness of the silicon has already reached the limit in SY technology. But with the CVD grown up largely at 2D materials, and actually integrate on the silicon technology, you get excellent devices. I don't know, probably Saptarshi Das is also one of the speakers in this conference. I don't know when he's speaking. Is speaking today?
Sir, we already had his talk.
Oh, yeah. So you must have seen. You must have seen some wonderful example of 2D on silicon or CMOS devices. So I think that is the future for the next 20 years or so.
Okay, sir. Thank you, sir. So on behalf of the IEEE community, I take the opportunity to thank our plenary speaker, Professor Samir Kumar Ray, sir, to take out his time and hours to share his expertise with us. Thank you so much, sir.
Thank you so much. I'll unshare my presentation. Yeah. Thank you.
Moving on to our next keynote session by Professor Kaniya Ahuja, Professor and Head in the Department of Economics at DAPP Indore. Now I would like to invite Professor Sehan Mukherjee to present the sapling to Professor Kaniya Ahuja to show respect towards nature. So please.
Sorry.
Thank you, Professor Mukherjee. Thank you, Professor Ahuja. Now I would request Professor Ahuja to please take over the session. So please. Slowly. It's my pleasure to give a short introduction about our speaker, Professor Ganiya Ahuja. Professor Ganiya Ahuja is a distinguished academician, economist, and administrator with more than 3 decades of teaching, research, and institutional leadership experience at Devi Ahilya University. He currently serves as a professor and head of at the School of Economics as well as Dean of the Faculty of Social Sciences. Professor Ahuja has played a significant role in advancing higher education, policy research, and academic governance through his contribution to UGC, ICSR, NAEC, and the Government of Madhya Pradesh. His research primarily focuses on tribal development, sustainable development, international trade, environmental economics, and economic governance. He has authored and edited several scholarly books, published over 100 research papers, and delivered numerous keynote lectures and invited talks at the national and international forums. His leadership in establishing research centers, academic collaborations, and policy-oriented initiatives have made him a prominent figure in the field of economics and social sciences in India.
Good morning, everybody. Well, I would like to congratulate you all for organizers for hosting this wonderful conference and to be a part of this event. This is focusing on very important talk how intelligent technologies are of the very important role very I'm a man of technology, I'm a man of economics, so I would like to integrate how economics, how AI technology and how technological development which are taking place in our country can integrate with various economic indicators and how these combined together can play an important role in building inclusive and sustainable development. So my talk would not be really technical, but it will be focusing on the navigation, the ways how AI can play an important role in sustainable development. Economics, we all are talking about it's a very different kind of code where you know that machine is learning. I know everything are able to predict something, robots are playing a very important role. AI is playing a very important role, and quantum systems are engaged in solving some complicated problems. So this is a very different kind of a world, and and digital platforms are also very importantly having their role in economic development. So things are changing, but at the same time, we all observe that there are inequalities are rising. The digital divide, the divide is already prevalent in rural India and urban India. There's a divide between man and woman. Urban and rural parents are there's a digital divide also. So climate change is posing a big problem. And when we talk about quality education, when we talk about healthcare system, there are a lot of things are taking place where I feel technology can play an important role. AI can really come up and have a very major role to play. If you look at the various technological innovations, the innovations which has taken place in our decade, we find that we started manufacturing with the help of steam engines. then we shifted to electricity, mass consumption. In the second technological revolution, in the third revolution, we shifted towards computerization and the automation system. And the fourth is this is the age of intelligent technologies, where we come across artificial intelligence, we come across machine learning, quantum computing, Internet of Things, and so many other interventions are taking place. But think is that how this is going to help us in solving many issues of inclusive sustainable development. If I go to the history of Indian economy ever since India became independent, if you look at different economic models which India has followed, we first had a era of labor-intensive technology. I mean, I should not use the word technology, but it was the era of labor-centric economy, and that was the phase of 1950s to 1980s, where we had a very primitive mode of production. We have very high level of illiteracy in the country. Technology was very low. That was a different kind of era, and then we shifted from this era to a technological service-led era of 1990s to 2010, and in 2014 onwards we shifted to digitalization. So the Indian economy has followed different phases. But if you look at these phases very closely, at the time of independence, it was a very poor economy. Mass production was not there. India was struggling for achieving the respectable economic industrial growth, respectable agricultural growth. But whatever technology we had, that was very primitive. So to go forward to navigate with this kind of technology was a very difficult task. So India has taken a stride in 1960 when we shifted towards a green revolution, and that was the era where the first technological intervention was seen in the Indian economy. And after that, we had long strides in 1990 when India was struggling with the balance of payment problem. India was struggling with a lot of debt problem. India opened to the LPG issue, liberalization, privatization, and globalization. And here India operates economy, and we shifted towards market-driven economy, and we adopted the global technologies for the first time in our system. This is where basically India opened to global technology. India opened to various IT sectors, and after 1991 and 2000 onwards, we are seeing the global IT sector in our country. After 2014, when India adopted digitalization, and after that, it's not a stop there. If you look at this phase of development of Indian economy, you find that India has realized that. Even if you look at the budgetary allocations of government of India over the last 4-5 years, you'll understand that government is spending handsome amount of funds on R&D and technology over the last 6, 7, 8 years. The government has also realized that yes, this is a field without technology, without research and development, nothing would. The traditional methods of growth, traditional modeling of growth and growth of the government, technology has to play an important role, and this is why, if you look at the allocation of government of India since 2019 onwards, you find that government is handsomely spending on research and development. They are making huge amount of fund. Capex has increased. Now the volume of capex is around 12.2 lakhs crores. That's a huge amount. And the share of technological funding, the share of R&D funding over the years has enhanced. So there have been major changes as far as the Indian economy is concerned. But now thing is that how this about digital era of 1914 onwards, we are living in terms of Aadhaar, in terms of UPI, in terms of DigiLocker, in terms of COVID and direct bank transfer. If you look at the volume of this digital transaction, they constitute around 48.5%, and the total volume per month is around 20 billion monthly transactions. As the UPI transactions are concerned, and they constitute around 24 lakh crore monthly. That's a huge stride as far as Indian digitalized system is concerned. So technology has been playing an important role, and technology has got to play a major role in the future also. Now, thing is that why when we talk about how AI is coming up and how AI is making us smile as far as Indian economy is concerned. I'm going to just present certain statistics and then I'll move forward to a very, very important aspect that why India needs AI and technological interventions in our world. So that I'll come to later on. But before that, I just give us little statistics about how AI is marking its presence as per the statistical data are concerned. Now, if you look at, there has been a change. We are not no longer government of India is no longer planning a strategy for AI, but government of India should from strategy to mission, and that's why India AI mission has been launched by government of India in 2024. And government is spending huge amount of funds on AI, adoption AI strategy. Why? Because India has realized that this is the era, this is the kind of technology which is going to play an important role, not only in the IT sector, but in education, in health, in all the social welfare schemes which the government is launching. So AI, the government has realized that this is the technology, this is the AI which is going to play an important role. And if I look at the, in 2024, government of India has launched around 10,000 plus crore rupees AI mission, and the focus was to make world-class AI ecosystem in India. And on these lines, 3600 plus AI deep tech startups and around 480 deep tech technological startups were launched by government of India, and there has been a steep change in the as per the approach of government of India is concerned after 2023-24 as far as intervention of AI is concerned. Now, the question comes in our mind is that why India needs AI interventions, and when we talk about inclusive and sustainable development, why do we require, why India needs inclusive and sustainable development? I'm going to highlight certain parameters which are key parameters for India. First of all is the poverty. India though has declined in terms of multidimensional poverty. So many people have grown beyond multidimensional poverty, but still India needs a lot of inputs, a lot of technical intervention as far as bringing poverty line below 40 to 50% with whatever. This is the share of poverty we have in India right now. So India has to work on this direction, and where AI and technology can play an important role. Unless we don't bring the masses under the domain of digital transaction, I think this poverty will not decline. So one of the prime areas is to work on poverty where technology can play an important role. India has been struggling very, very hard ever since independence, and even now after 78 or 90, 79 years of independence with inequalities. Inequalities are not only confined to economics, inequalities and urban and rural, but man, woman, everywhere. You find a lot of inequalities are there, income inequalities are there, wealth inequalities are there. So if we have to really overcome these inequalities, then technology and AI interventions are another very, very important aspect are employment. India has more than 90% of our dependency has been on unorganized sector. And unorganized sector has no ingredients of technology at all. If we really want to carry forward this country on the benchmark of becoming a developed nation in 2047, then I think unorganized sector has to be a lot of interventions. AI has to play an important role. Technology has to play an important role, because this sector has been neglected, and this sector has always had lack of education, lack of literacy, and lack of technology. So if we want to really enhance the employment scenario in our country, then unorganized sector need to be inducted with a lot of AI intervention. This is very, very important aspect is that, agriculture sector, we have more than 55% of our workforce depends, but their contribution is only 40 to 15%. This sector needs a lot of interventions, because agriculture sector, if you look at the total food production in our country right now, we have surplus food production which will feed the whole nation for the next 1.5 years. It means our dependency on agriculture sector is immense. But this sector now needs a lot of interventions when farmers bring their crops in the mandis do not provide them the right kind of price. So price mechanism can be AI price mechanism can be established with the help of technological interventions. The farmers know the right kind of price of their crops, then they will be able to enjoy better benefits. But what has happened is that they don't enjoy that benefit because the e and other mandis do not provide them the right kind of price. So now, if you look at the scenario, there are a lot of prices, and those prices are confined to crop failure. Those prices are confined to market failure. So this is where even agriculture sector needs a lot of technological interventions, a lot of AI intervention, and I think this is going to play an important role in coming days, in coming decades. If the government works on establishment of warehouses, establishment of processing units, and establishing very amicable marketing system where the AI and technology can club together, and they can provide a platform to the farmers, where farmers get the right price of their crops, so then we can have a sustainable agriculture. Another problem which agriculture in our country is facing is that there is a lot of water depletion in our country. If most of the area we find that the groundwater level has gone very down, it's around 500 to 600 feet, and farmers are extracting water to the ground. So now it is, water mapping is very, very important. And when we talk about water mapping for sustainable irrigation development, then AI can play an important role. Technology will play a very, very crucial role. So this is another area where I think that yes, interventions are required, and India is thinking of becoming a Viksit Bharat, and India is the theme of converting its development model into inclusive, sustainable initiative. Another very, very important role is when COVID-19 came, I always quote this example. When COVID-19 came, it made India very, very embarrassed, because the kind of health sector which India had, we were depending on China. Most of 70 to 80% of our needs were imported from China. We were not self-sufficient to take care of our healthcare system. So now I feel, and if you look at this statistics is very important. As per the current statistics, we have one doctor in the population of 1,500 people. As per the WHO says that India must have one doctor among 1,000 population. So still, India needs more. India lacks 50% of the needs of doctors and nurses. So this is where AI can play an important role. Technology can play an important role. We are talking about telemedication. We are talking about operation and surgery with the help of AI. So this is where interventions of AI and technology has to play an important role. Man can be replaced with machine, and the man can be replaced with technology if that technology is affordable and amicable. So this is another area where I feel the coming decade, the next decade is very, very important, because whatever even technology development should not only confine to IT sector. I always say that if a technological advancement is taking place, that should also take care of health, that should also take care of education, that should also take care of human capital formation, that should also take care of peer development. It should not only confine to IT sector. So these are the interventions which are also needed as far as health sector is concerned. India has already signed a Paris Agreement where India has to make its land zero emission free. I mean, by 2070, we have already signed Paris Agreement, and this is a very, very challenging step for India. And this is where how we can convert our initiative from fossil fuel to renewable energy. And we are working very, very hard on that ground. Now, at present, we are producing around 230 gigawatts of our electricity. By 2025-26, our objective was to meet the 500 gigawatts production of electricity with the help of renewable energy. And this is where India is committed. As far as India is concerned, other nations in the world are concerned, India is really taking a very serious step in order to shift from fossil fuel to renewable energy. This is very, very important, because if India is committed for environmental sustainability. Another very important aspect is that, We have seen in India there are many states in India who have been doing good in terms of growth. If you look at Maharashtra, if you look at Punjab, if you look at Gujarat, if you look at Rajasthan, some of the states are very good as far as the economic growth is concerned. But the same these states are very poor in terms of environmental growth. They have not really taken care of environment. Now the time has come to be, if you are thinking of inclusive development, if you are thinking of sustainable development at a national level, then growth must tie up with the development environment. You cannot neglect environment. So there has to be a proper integration between growth and environment. And this is where AI and technology and R&D can play a very crucial role. And that is what the government has realized. Last couple of years, looking at the budgetary allocation of government of India, last 4-5 years, they have been substantially allocating good funds in the areas of eco-friendly environment in terms of environmental sustainability. This is very important. It's a population is increasing and more people are shifting from rural belts to urban belts. But the contribution, the way these urban bodies should be taken care of, India is neglecting urban development. Urban development is including, except just keep some major cities on the different side, but most of the cities in the country are not being taken care of. So if India is really planning for urban development, India is planning for having a strong urban local bodies, then there are interventions are required, and here the technology can play an important role. If we are talking about urban development, if we are talking about a very conducive urban planning for India, then AI and technology and research and development can come together, and they have to play a very crucial role. Now it's an era. It's a time when we must invest in building institutions. Without building institutions, growth will never be sustainable. Whatever we can dream of, if we don't strengthen our institutions, then this kind of growth, this kind of development would never be inclusive. So this is another direction, whether we talk about RBI, whether we talk about World Bank, whether we talk about WTO, whether we talk about Asian Development Bank, whether we talk about International Monetary Fund, whatever institutions we talk about, the world needs strengthening of these institutions. I mean, these institutions should be beyond political intervention, and these institutions can serve the society. These institutions can play an important role in bringing inclusive sustainable development if we have proper intervention of technology and AI in that. So this is a very important aspect. Another. I'm going to present some very important statistics. India feels so proud that we have a demographic dividend. We have a youth population of 65% of our population is below 35 years. And the median age in our country is 28 years. If you look at the median age of Japan and other countries in the world, you find that they are above 45 years to age. So India is enjoying demographic dividend, but I believe very frankly this demographic dividend is going to be a liability on us if we don't inculcate the right kind of skills. What kind of skills? We need smart skills. We don't need very ordinary skills. If you want to build India, if you want to build inclusive India, if you want to develop sustainable development in our country, then demographic dividend needs to be skilled. If you don't focus on skilling demographic dividend, then the whole exercise is going to be a total waste. And this is where IIT, the IIMs and the top institutions are playing an important role. They are working on development of those skills, and they are really playing an important role in inculcating the right skills among the youth who have joined their institutions. And this should not be confined to only IIT. This should not only be confined to only IIMs. The other institutions in the world should not only be a place where degrees are offered. No, we don't need young folks which have degrees. We need young folks which are well equipped with technology and with learning initiatives. So that is where we need to play an important role. And these statistics which I'm going to present before you are very alarming. 43% of graduates in our country are not employed. This is not my data. This is the current data of 2025. 43 to 44% graduates in our country are not employed. This is a big question mark on our education institutes. And this is where I believe technology, R&D, and AI has to play a major role in health sector, education, and human capital. And this is where we need more interventions. And this is also very important. 65% of the workforce has never ever gained any training in their life. 65% of the workforce has never ever gained any kind of training programs in their life. So it means whatever they're doing without any training program. So that kind of a labor force can survive for a couple of years, but that kind of labor force cannot build the future India. We need more and more training programs, we need more and more interventions. And there's a mismatch. India has been experiencing the mismatch. Whatever has been taught in our classrooms and whatever the industry requires from our youth is a mismatch. And only 8.2% of, this is not my data, this 8.2% of skills are matched. Remaining 90% of skills do not match what students learn in a classroom and what they have to display in their workplace. So there's a big difference, and this kind of growth, this kind of building, this kind of, we feel so proud we have demographic dividend, but this kind of demographic dividend would be a waste. Not serve the nation. If you're thinking of building an inclusive India, if you're thinking of building a sustainable development, then I think there are big question mark on this area. So if we are shifting, we are going away from we have first made a move from a labor intensive growth to exports intensive growth. Now India is forwarding away from export incentive growth to AI incentive growth model. Then I think a lot of interventions are required as per the scheme of our workforce is concerned. And I don't know how many of you have worked with the ACE report. I'm question marking on the basic education in our country. A student in 7th class cannot read the book of 2nd class. A student in 7th class doesn't know how to solve a problem of mathematics in 7th class. So what system we are developing? Our education system is more concerned about scholarship. Our education system is more concerned about whether we reach certain people. I'm not against that. At the same time, what about the skills? What about the quality standards? This is where we need interventions beyond political interventions. We don't need political interventions. We need real-time interventions in the terms of right kind of technology, right kind of skills, right kind of AI intervention, which can really inculcate the right kind of skills among students at a school level and as well as at university level. So this is very, very important. Now, what needs to be done? We need, now, I think you must have already gone through a lot of, this has been a talk nowadays that yes, AI should play an important role from a school level. AI learning should be introduced at a school level. And this in university must be made compulsory. Yes, there are many universities, many colleges which only teach a tailor-made syllabus in the classrooms. No, we don't need that. We need digital skilling. That should be a part of our curriculum. And more practical exposure is required rather than comparing the course. No, we don't. Some institutions are doing great job, but most of the institutions are in our country are not focusing on this aspect. And India need district level AI hubs everywhere. India has to really play an important role in the future. If India really want to create itself as a education, AI education hub, then we need district level AI skill centers in the country, where every youth can join and upgrade their skills. So these are the interventions which are required at a district level. One change which is very remarkable and which needs attention of all the policymakers in our country. If you look at the work participation rate in our country, the work participation rate, the population which is engaged in agriculture. This is very important. I request you to kindly have attention on this. The work participation, the workforce which is engaged in agriculture, that ratio has been declining. People are no longer working, happy working in agriculture profession. They're shifting from agriculture to base-based profession. And the percentage of people who are engaged in agriculture in rural belts, they are declining, and the percentage of base-based people is rising. So now if our rural structure is like that, where most of the population depends upon agriculture, but the share of workforce is declining, then how we can absorb this, this workforce which is shifting from agriculture to wage-based professions? This is where we need interventions even in the rural belts. AI should not only confine to urban belts, AI should not only confine to IT, AI should not only confine to ADAMS, AI should not only confine to AAB or any other institution. Yes, give me 5 minutes. AI has to play an important role in building this AI structure even the rural belts. We need to create this structure so that the rural people don't need to move to the urban belts, they can get a better job, they can get a different kind of job, which the people are shifting from agriculture to non-agriculture profession so they can have a better jobs in rural belts also. So this is where I think AI and technology can play a very, very crucial role. Another very important thing is that, you know, and I've already spoken about smart agriculture. Uh, if you look at in the work participation, I was talking about the share of women in our work participation rate is around 41%, some data says 38%, some data says 49%, some other reports say 41%. And the share in the population is around 50%. But the share in the work participation is 38 to 31%. Where the male counterpart is about 60%. So there's a big difference as per the work participation rate in male and female is concerned. And India is thinking of becoming a sustainable destination. India is thinking of becoming a developed nation. Then I think the contribution of women in workforce is going to play an important role. More and more, based entrepreneurial development is required. More and more, and I think very frankly, this is a severe problem as far as urban development is concerned. The share of women as a workforce in urban is declining faster as compared to the rural belt. That's a big question mark on our development model. So I think this is where we need to provide them a very conducive AI or technological level environment so that women can also become entrepreneurs, women can also contribute to the GDP environment. And one more area, we have always talked about GDP. We have never talked about what happens beyond GDP. The contribution of a woman. Woman's contribution is not counted because the woman's contribution is only counted when she works in the office. Her contribution in building the family, in building the society, that is not been marked. So this is where women can work from home, and women can play an important role being at home only. So where technologically led enterprises can be established at the workplaces at homes, and they can also play an important role. So these are many there are a number of dimensions which need to be done. But yes, with all these sides, so with all these points which are made, I'll just some of the things that yes, India has a potential of becoming a developed nation. India is playing a very, very crucial role. India has realized that the development through technology and development with the help of or other integration of AI is going to be a very, very crucial role in the next generation. If India is dreaming of fulfilling sustainable development goals by 2030 and later on becoming a developed nation by 2047, then we have a couple of things which I would like to put before you. Number one, we have a very conducive, that's one way. We have a very conducive democracy, We have a very, very strong democracy which has always made India proud. So this is where, and we have enough surplus as far as, whatever crisis took place at a global level, economic crisis, India has always come out of that. Whether that was Ieee in 2008-9 or whether the current crisis which are taking place, but India is playing very, the kind of geopolitical intervention which India is marking on a global front, and that is something which places India much ahead as compared to other countries in the world. So I think India has got potential, India has got a lot of capability, and we should have faith in our workforce. But yes, one thing which is going to play an important role is that we need to scale the workforce. Without scaling the workforce with smart technology, without AI enabled and technologically enabled technology, will not serve the purpose. So we have to invest in technology, we have to invest in human capital. Thank you so much.
Thank you, sir. Such an informative session. Now I would like to request Professor G.S. Kumar sir to present a memento for speaker Professor Ahuja as a token of appreciation and gratitude. On behalf of the ITC community, I take the opportunity to express our heartfelt gratitude to Professor Ahuja for taking out the time and efforts to share his expertise with us. Moving on to our next invited session by Professor Arnab Datta in the IIT Roorkee. I'd like to give a short description about Professor Arnab Datta. Professor Datta is presently a professor of microelectronics and VLSI affiliated with the Department of Electronics and Communication Engineering at the Indian Institute of Technology, Turkey. He received his PhD degree in electrical engineering from the Indian Institute of Technology, Bombay in 2010. His research interests include fabrication, characterization, and modeling of smartphone devices. He is also developing components of other silicon components, including absorber, color filter, and grading. We are grateful to you, sir. Now I would request Professor Anand Datta to please take over the session. Sir, please.
Can I speak from here?
Yes, sir. And just sit here.
Yes, I just stand and do that. Shall I move this chair up here? So I can leave it here.
We need a chair.
No, I don't make it. Yeah. So, good morning. Thank you.
The mic users so that.
Yeah. So, good morning. Thank you, organizers, for inviting me here, especially Professor.
Sir, we need to go it users.
Hello. Good morning, everyone. So, first of all, I wish to thank the organizers of the conference, especially Professor Pallavi, for their kind invitation. I'm very happy to be in the campus, IIT campus. Yesterday, we had a nice visit campus too. And so today, this talk would be slightly technical. So that, as you can see, the title of the talk, that engineering the tin oxide through the germanium incorporations of the thin film transistor. So it is part of the research activities which we are doing at the IIT Roorkee. My students are actively involved in this, the thin film, the transistor technology, the development. And so I'd be highlighting some of this recent research in this thin film transistor, especially the tin oxide based channel materials. So here comes the motivation of the talk. So the thin film, the transistors are very much useful for the backplane of the organic light emitting the diode OLED, the displays. So it is one of the important ingredients, especially when you see any of the flat panel displays. Say for an example, this laptop screen. So there is a back panel of the TFTs that is driving the pixel arrays. And then the display is visible here. Okay. So therefore, and the key ingredient for this, the thin film, the transistors or the oxide, the semiconductors. And the table is very interesting. See, pointer. I will change the slides. Or no. Maybe the pointer more. Okay. Just a minute. That's also correct. Should work. I think we can take it to pointer too. Yes.
This is a very much. Should I
Yeah. Just a minute. Can I say here? Easy for me then. Oh, wonderful. Yes, this is true. Yeah. Okay. So as you can see in this table, so there are seconds. So I will share the screen. Just do it. Is it fine now? Yes. Can I start? Just first one. So no issue. No issue. So as you can see in this table, so there are the various cations which are used for the development of the oxide, the semiconductor. And out of that, the blue colored one are very much interesting. So blue colored one are gallium, the zinc, indium, and the tin. So these four elements are very interesting. So because they have the bigger s orbitals, so that can contribute to the formation of the conduction band, and that will be helpful for the electron the transport. On the other hand, these materials, that arsenic, cadmium, mercury, the thallium, and the lead, so they also can contribute to the s orbitals and therefore to the formation of the conduction band. But the problem is that these are health hazardous materials, so therefore they are usually avoided. And the rest of the materials, the copper, the silver, gold, and so these three materials particularly, so they can have a p-type conductivity, especially for the oxide semiconductor. Having p-type conductivity is very much the challenging. And on the other hand, the p-type conductivity is required when you want to develop the CMOS circuits. All of you know that, because for the CMOS circuits, we need an NMOS the transistor as well as a PMOS transistor. And so now the issue is that now mostly people are working in these four materials: zinc, gallium, indium, and the tin. And so combining these three elements, the indium, gallium, and the zinc, a fantastic material has been synthesized, which perhaps you might be knowing that is indium, gallium, zinc oxide. And that is very much a hot topic for the development of the displays. Now, my talk would be focused on the other hand. So I took this material, the tin, because it is widely available, and the tin oxide can have the two types of conductivity, which is very much interesting as compared to the other oxide semiconductors. Most of the oxide semiconductors are unipolar material. Either they exhibit N-type conductivity or P-type conductivity. But by controlling the phase of the tin oxide, either it's monoxide or the dioxide phase, you can have you can have both P-type and the N-type the conductivity. So that is why this material, the material is very much interesting. On the other hand, so for development of any amorphous oxide, the semiconductor, you need to satisfy these two more criteria. One is a low temperature deposition, and second is a large area deposition. So naturally, when you talk about a very much big flat panel display, say for an example, your television screen. So think about that is a 75-inch screen. So there are so on that large area, you need to deposit uniformly the material, and finally you need to pattern to make the transistor. So therefore, the large area, the deposition is one of the criteria. And why the low temperature is important? Because the flat panel displays are fabricated on a plastic panel. So therefore, if you increase the temperature, which is mostly required to activate the material, so to improve the conduction, so naturally that process you cannot do it on a plastic substrate. So therefore, low temperature is one of the requirement. And the bipolarity, as I told, most of the amorphous oxide semiconductors are unipolar, but tin oxide is bipolar. That I will be discussing here in this talk. And the fourth criteria is optical, the transparency. So many of these amorphous oxide materials, they have a DD, the band transition, and so that actually absorbs light. But what happens, so if you look at your flat panel display, so there is a backlight available at the back end, and that goes through the TFT panel, and finally you can see the display at the front plane. So therefore, unless the material is optically transparent, you cannot develop this technology. So therefore, these are the 4 criteria which you need to meet basically before selecting a material. Now, one idea is like for many generations that amorphous silicon had been the used in the development of these thin film transistors. But the problem is that amorphous silicon it uses very much high temperature. So obviously it cannot satisfy this criteria. And the second is the mobility of the amorphous semiconductor is very much perturbed by this band structure. So typically they have an sp3 orbital, but when you have an amorphous material, there is a local distortion present, and that can cause a hopping conduction, and naturally the mobility is affected. On the other hand, if you take this metal oxide-based material, they have the bigger NS orbital, and electron can easily go through, despite if there is any the bond angle variation. So that is a point like why you prefer using this metal oxide as the material channel material for the TFT. And so there is a huge research activities going on in this oxide semiconductor area, and there is the market volume is also very high, especially for this display technology. And all of you are aware that Government of India Prime Initiative like National Semiconductor Mission, that one of the initiatives is developing the display technology like homemade technology. And so doing that, so this TFT development is very much important. And so, and therefore, so this work is that way very much relevant. And you can see that, like, this would be the outline of my talk. And now, directly coming to the material development, as I told, it would be slightly technical what we are doing actually for the this material side. So basically, we took the tin oxide material. It is a co-sputtered material. So we use the tin, the target, and the co-sputter with the germanium. Basically, we tried the germanium doping inside the tin oxide, and why we did so, that we will be discussing in the part of this discussion. That we have seen that if we control the oxygen, the pressure, or rather the flow rate ratio to 4.33%, and if we sputter the tin in the presence of the oxygen under this condition, the target power is 100 watt. So we can have the tin oxide phase. So which you can see, the tin oxide is this red color. So this tin oxide peaks are visible, right? So we do not have any germanium in it. On the other hand, if we co-sputter germanium in the same condition, the oxygen, the percentage condition, we also have some germanium. We also have the germanium, the oxide, the phase present when the germanium, the target power is high. You can see that from here, that some germanium, this cyan color. So some germanium is present, and that basically distorts somewhat the crystallinity of the tin oxide. And at the same time, some of these phases of the tin oxide phase, SNO2 phase, is the green color, the symbol. Okay, so therefore, in this condition, both the phases are present. SNO phase is present as well as SNO2 phase is also present, and some of this germanium phase is also present. On the other hand, if we change the recipe to oxygen by argon ratio to 12%, so you can see that SNO phase is not present, rather you get the SNO2 peaks. The dotted color are the SNO2 peaks. So these two phases of the tin oxide are very much important. And by the way, we did the post-deposition anneal at 450 degrees centigrade in nitrogen. So that can make this transition between the monoxide and the dioxide phase. And why these two phases are important? Later on, I will be showing you that this monoxide phase is contributing to the p-type conductivity. On the other hand, this dioxide phase is contributing to the n-type conductivity. And as I discussed in the beginning of the work, that getting both the types of conductivity is very much challenging in a single oxide semiconductor. And that way the tin oxide is very much interesting. And now that what is the implication of the germanium, the doping? So that we have seen here. So we did some XPS analysis. We have seen that if we look into the first recipe, that is 4.33% oxygen to oxygen by argon ratio, that we have seen that when you increase the germanium, the target power at the time of deposition, you can see from here this SN3D peak has been decomposed into the different oxidation states of the tin, that is SN0, SN2 plus, and SN4 plus. And you can see that the SN2 plus phase, so that is SN2 plus oxidation number. So initially it was high for the germanium 0, that is when there was no germanium present in the film. Now when you increase the germanium, the SN2 plus proportion is reducing. Okay, so it is going from 82% to the 67%. On the other hand, if we use the second recipe, that is oxygen by oxygen to argon to 12%, you can see that SN4 plus, that is a 4 plus oxidation state of the tin, so that is going to be reduced. So from the 73% to the 60.89% when you have the higher the germanium power. The reason being is that the germanium also belongs to, it is also a group 4 element like the tin. So therefore, it can also have the same oxidation number. It can stay in the oxidation number 4 as well as oxidation number 2. So when you do the deposition at the 4.33% condition, the germanium 2 plus can substitute the tin 2 plus atoms in the host lattice. And so therefore the tin 2 plus, the number is reducing. On the other hand, we did the germanium 3D deconvolution also. You can see that here the germanium, the 2 plus is increasing from 1.74% to 18.63%. It means that germanium 2 plus is increasing and the tin 2 plus is reducing. Then why the tin atoms are basically going? Basically the germanium is substituting to the tin sides and the tin is displaced, and by this ionization process it is releasing 2 electrons, and then these 2 electrons are basically reducing the tin 2 plus to make the neutral the tin atom, and that you can see the evidence here. The tin atom is increasing from the 7.60% to the 25.19%. So therefore, there is a significant amount of the tin atom present in the germanium doped film. Similarly, the same thing is happening here. The germanium, the 4 plus state is replacing the tin 4 plus state. So therefore, the tin 4 plus is reducing, and the germanium, the 4 plus, that is increasing. You can see from here, 71.87 to 78.78%. And the 4 electrons it is releasing by this ionization process, that is reducing the tin 4 plus to the tin atoms, and there is a significant increase in the tin atoms from the 3.43% to the 13.10%. So therefore, basically, when you dope the material with the germanium, it is working as an isoelectronic dopant. Isoelectronic dopant means the germanium atom is replacing the tin atom in the same valence state. That is basically the isoelectronic doping. And now the question is, what is the advantage of this germanium isoelectronic doping? So we did the whole measurement. We have seen that when you do this isoelectronic doping by the germanium, by the first recipe, you can see that Hall mobility for the holes are significantly increasing. So it was around 1 centimeter square per Bohr second in the undoped film, and that went up to close to 5 centimeter square per Bohr second for the germanium doped film. And on the other hand, you can see that the number of holes are also increasing with the germanium doping. And this evidence we got, like we did the UV, the photoemission, the measurement to profile basically the Fermi energy level and the age of the valence band. You can see that as you increase the germanium, the target power, the Fermi level is becoming closer and closer to the valence band. And that is the reason why the number of holes are increasing here. And now the question is why the mobility is increasing. The speciality of the tin oxide is that it has, I'll be showing it in the later slide, so that we can show it here, that we did the material modeling by using the ab initio tool. And you can see that, so here are the different orbital contributions, SN5S, SN5P, and O2P. Basically, SN5S, that is this orange color, and is oxygen 2p. So these two are contributing to the valence band. And unlike the many metal oxides, so where the O2p majorly forms the valence band, but in case of the tin oxide, SN5S also has a contribution, and they hybridize and then make the valence band. And you can see that because of this hybridization, so that overlap with the germanium base and the SNS is higher near the valence band edge when you have the higher germanium doping, and obviously that contributes to some of the delocalization of the bands, and that can increase the mobility of the carriers. That is one of the reason. And the reason is that we found that because of this higher number of the tin, so that also can create the strain in the film, and so that also delocalize the valence band, and that increase the mobility of the carriers. And the second thing is that when you use the second recipe, you can see that the density is reducing, unlike the first recipe. Electron density is reducing. Maybe it looks at a first glance, it looks bad. But you can see that from this UV photo emission, the spectrum measurement, you can see that Fermi level is moving away from the conduction band edge. So it means that the concentration is reducing. Okay, I'll be discussing this implication later, whether it is good or bad. For the time being, you can see that the electron mobility is also increasing. The Hall mobility for the electrons are also increasing significantly. You can see that it is close to 16 centimeters per volt second. These figures are quite impressive for the amorphous oxide materials. And that is an advantage, like with the germanium doping, both the carrier mobilities are increasing, hole density is increasing, electron density is reducing. And we can control the bipolarity by means of the germanium doping. That is interesting. And similarly, here also, the electron mobility, why it is increasing, that we calculated through this ab initio model. You can see that here, SN5S and SN5P, they are contributing to the conduction band. And similarly, if you take the overlap of the germanium AS and the SNS, you can see the states are populating near the conduction band edge. It means that, so the germanium some way helping the delocalization of the conduction band states, and that can improve the electron mobility. So it is just an inverse the phenomena for the other case, like when you change the recipe, right? And now this specifically for this in the N-doping recipe we have used to fabricate the thin film the transistor devices. Here are the process steps that which we fully did at the IIT Roorkee. So most of these processes are very common to you. That we clean the substrate, and then you have in the atomic layer deposited hafnium oxide. And this hafnium oxide deposition we did it from the IIT Roorkee facility. And then we have the tin oxide, the channel, we patterned that. And then the top of that, we patterned the source and the drain contact. And here is the FSM image of the transistor that we fabricated. And we did XPS analysis to see that how much is the germanium is present for the different recipes. And it can go up to 12.2%. And after fabrication of this device, we did some of the standard IV measurement and the bias stress stability and many other things we did. And that I want to summarize here. So first of all, if you remember correctly, that with higher germanium doping, the electron concentration was reducing, but hole concentration was increasing. Now the question is why electron concentration is reducing. You can see that if we take the 1s, the deconvolution, you can see that basically the oxygen vacancies, it are reducing from the 26.13 to the 12.29%. So why it is like that? Because the germanium oxide, the formation enthalpy is much higher than the tin oxide, the formation enthalpy. So therefore, in case the germanium substitutes the tin from the lattice and bind to the oxygen, it is very difficult to break the germanium oxygen bond. And that is why it is reducing the oxygen vacancies. And especially for the oxide semiconductors, oxygen vacancy contributes like to the electron release. So you can typically say that one oxygen vacancy contributes to 2 electrons. And that is why that with reduction of the oxygen vacancy, the electron concentration is the reducing. And one important aspect you can see from here that if you take the IV characteristics for the higher germanium doped film, because of the lower electron number, the leakage current of the transistor is very small. And that is obviously very good. And that helped to improve the ion to I of ratio of the transistor. And this figure is quite impressive. We went up to 10 to the power the 9 I of 2 ion. I on to I of, sorry. And on the other hand, we have seen the subthreshold slope of the transistor is very good. That is close to 78 millivolt per decade. And there are some, you can see that there are some humps present here, and that we are working currently, that subthreshold part modeling, and that is a separate part of the discussion. And the thing is now, you can see from here that now the question is, now this transistor with the higher the germanium doping, its on current is also very high, despite the fact that electron concentration is slightly compromised. So the reason being that we did the WH fitting from the XRD, and we have seen that when the germanium is substituting the tin atoms in the lattice, you can see that the slope is negative, the beta cos theta and 4 sin theta, and it is increasing with the higher germanium doping. The slope is increasing and it is negative. It means that by the substitution, the germanium is creating the compressive strain inside the lattice, and that improves the mobility of the carrier. If you recall, the on current of the transistor, it depends on the number of carriers as well as the mobility. So therefore, both the parameters are very important, though the number is slightly compromised, and that is good for improving the offstate leakage of the transistor. At the same time, the mobility of the transistor is enhancing, that is improving the drive current of the transistor, and that is why we are getting, like the high onto the off ratio. And we did the photoluminescence also of this film. So you have seen that like there are a couple of photoluminescence peaks are available out of the radiative recombination. So 368 and 470 nanometer and 516 nanometer. Mostly they are related to the oxygen vacancies. This is single oxygen vacancy, that is surface oxygen vacancy, and it is the direct, the band-to-band, the transition. And these vacancy peaks have the contribution to the reliability of the transistor as well. And that is a second part of the discussion. So you know that when the transistor operates in a circuit, we need to stress it for a long time. And yeah, sure, I will grab it. So, so therefore, if you give the positive and the negative, both the bias stress, you can see that with positive stress, the threshold voltage is the shifting in the positive side. On the other hand, negative stress, the threshold voltage is shifting in the negative side. But in case of the higher germanium doped transistor, the shift is very much less. The question is that in which way the germanium doping is also improving the bias stress reliability of the transistors as well. We did some variability studies here. And the idea here is that basically that these trap states, which I discussed before, you can see that this PL peaks are for the higher germanium, the doped films, they are subdued actually. And therefore, there is a less carrier trapping inside these oxygen vacancies. So basically for the positive bias stress, there is a chance that electron get trapped inside the bulk film, and that possibility is reduced. So that is why you get a less voltage or threshold voltage shift in the positive bias stress. On the other hand, in the negative bias stress, that VO plus vacancies ionized into VO2 plus, and cause a relaxation in the lattice. And since the number is less and the ionization is less, that is why we get a less negative bias stress shift, the threshold voltage shift. And that is good, in fact, for the long-term transistor operation. And we did like the modeling here, like the threshold voltage shift is fitted with the stretched exponential models. And we calculate the trapping and detrapping parameters and that exponents. And all the way that we have seen that higher germanium, the transistors, SNO2 films are always good in terms of the reliability as well. We did the PBIS and BIS, the characterizations as well, the bias and the illumination stress. Because as I told you, the TFTs are subjected to the, like for the for this that white irradiance always falling on it. Like if you look at the back plane of your flat panel TV, you can see that a white light is glowing here at the corner, and that is always illuminating the TFT, and it is going under continuous illumination stress. And that way, the germanium doping, because of the less carrier trapping, so it helps to reduce it helps to improve the basically NBIS and PBIS characteristics. Now the thing is, like, that is the last part of my discussion. Now you can see that we with the germanium doping, we simulated the band structure of this material, and we have seen that the band gap is the direct band gap at the gamma point is reducing with the germanium doping, becoming the 2.88 electron volt. Therefore, these films are also very much optically sensitive, and we used it in case of the designing a basically element for the reservoir computing and the synapse. The whole idea is that this is the computing block. You can see that there is a reservoir layer, input layer, and the output layer. Input layer takes some information and passes it to the reservoir layer, does some computation here, and at the output layer you get the information at the output. Now the question is, what is reservoir computing and how does it how it is different from the synapse based STTP learning basically. So the reservoir computing basically it depends on, suppose there is if you are detecting some fast varying signal, suppose a car is moving or some flash of light or something, some time varying event you are detecting. So then you always prefer the reservoir computing so that you can save basically a lot of time. So the reservoir states, so therefore it should quickly respond to the input signal and accordingly that take the decision. And so for that you can see that, so therefore the time scale of this the relaxation control is very much important. So those of the devices, those will be making this reservoir layer, and that you can do it by the RAM as well as a thin film transistor. We are trying this work by the thin film transistor. Basically, we took the same transistor with a different germanium doped layer, undoped layer to the heavily doped layer. You can see that in case there is no doping with the germanium, so it's the photoresponse is the slowly decaying, right? And on the other hand, if you increase the very much germanium doping, you can see that it is quickly the decaying. So the state is becoming the volatile, and this state is the non-volatile. And in between, so the state is the moderate, the volatile, which you can control by 5.5% the germanium doping. And we have extracted the subcap states of the films, and we have seen that in case of the undoped germanium films, the subcap states are very much higher compared to the doped germanium film. And the subcap states, when the carriers are excited and it trapped inside the subcap states, it takes lot of time to release this carrier, and therefore you get persistent photoconductivity, and that holds the state. And this non-volatile nature of the transition computation. On the other hand, if you want reservoir computation, just 1 minute. Yeah. So if you want to do reservoir computation, then the state should be not strongly volatile, but moderately volatile. And that we can control by the engineering this channel. And so here we took some examples, like that is the last part of the discussion, that we took the 4-bit optical pulses, designed it from 0000 to 1111. You can see the two states, it is shown here clearly, 0011. In case it is undoped, you can see the 0011 means that 00 and 11. So there is a potentiation here in case of non-volatile state. You can see that it is a potentiation, right? On the other hand, if we have the moderately doped channel, you can see that it is 001, and then for the next one, the state is slightly decaying. Okay, it is not perfect potentiation. On the other hand, if you have very heavily doped channel, the 0011, that is 00 and 11, the state is latched here. It is not a potentiation. So therefore, reservoir for the one more example you can see from here, 1011. That is 1011. There is a potentiation here. But in case of 10, it is going here, not fully decaying, and then 11. Okay, but here you can see it is 1011. It is latching here. So therefore, so these moderately doped the transistors are very much useful for the RC, the computation. So that it can that couple the previous state to the next state, which is not possible with the heavily germanium doping because it is forgetting the information. So this work we are going currently to do some computational exercise, and so basically we are optimizing the channel material and the device engineering and everything. Now the conclusion of this talk is that first of all, the tin oxide is a fantastic material. I would say that because it shows the bipolarity, and that is good for the CMOS circuit development. The only hindrance is that the tin oxide mobility is very much restricted. And in this work, by controlling the germanium, the doping, and the developing the new recipe, we have achieved like a significant ion to I-off ratio and the good subthreshold slope. This figure is quite impressive, and the good field effect mobility. And on the other hand, the germanium doping also helps to improve the reliability of the devices for the long bias stress and the bias elimination stress operation. That is obviously very good. And the final point is that this the germanium dope, the TFT channel, can be used for the reservoir computing, where you need to detect the first varying signal. Okay, unlike the synaptic, the computing. And so that way, like this development is very much promising. And the last work, it is slightly confidential that this paper is accepted and we are going to present in the device research conference in Ann Arbor, Michigan in this the next month. And this, in fact, in this month. And that part of the results I have shown, not everything I have shown, but it has a tremendous possibility. And I wish to acknowledge my research scholar, Joy and Suman. So they are PMRF research fellows, and the most of the work I discussed here, that is majorly done by them. Of course, I advise their thesis, but it is the work-wise majorly they did many of this work. And some the demonstration of our fabrication facility at IIT Roorkee that we are developing at IIT Roorkee. And if you, I welcome all of you. Please come who are interested to see our facility, and we can do collaborations specifically in the TFT and the RAM area, that related developments. Okay, thank you very much.
Thank you, sir. Thank you, sir. Thank you, sir, for such an informative and very elaborative session. I will
Excellent talk. Now, so how do you control the P-type doping? Like I know you're using certain targets.
No, we are using the tin target, and it is a reactive sputtering. As I told that we are controlling the oxygen flow, so the 4.33% oxygen to argon, that is very crucial. If we take it to the 12%, then we get the SNO2 phase. And this phase we confirm through the XRD analysis. Only thing is that when you dope it to the germanium, we do the co-sputtering, and we did the Hall measurement, and then we have seen this the mobility is improved. But this oxygen control is very much important. We have the tin target only, not a tin oxide target.
thank you, sir.
So
Now I would like to invite Professor Rita Banerjee to present a memento to our esteemed speaker, Professor Arnav Datta, at the token of appreciation.
right.
Thank you, Professor Banerjee. Thank you, Professor Datta. On behalf of the IEEE community, आ जाओ थोड़ा सा कैबिन में बंद करना क्या
Start. इसमें रिकॉर्डिंग वाला चल ही रहा है। इसमें रिकॉर्डिंग भी चाहिए। हाँ, रिकॉर्डिंग सब चल रहा है। ये मेरा हो गया। मैं तो आई भी नहीं दे रहा है भैया। क्या बोल ठीक है, रिकॉर्ड भी नहीं कर। वहां से तुम गोबर को गए हैं। हाँ, टॉप गए लास्ट में। ठीक है, गए लास्ट में करना नहीं है। Session title. पूरा चेक कर लिया है, सब कर दूं क्या अभी?
तो लगा के क्यों उसको मिनिमाइज करके
Yes. Yeah. Yes. हाँ Right. Yeah, चल रहा है, सही चल रहा है.
क्यों आपने गूगल मीट बंद कर दी क्या?
It's just a family. It's a family. Who said it? It's a person. जी इसे बड़ा थोड़ा काम कर रहा है
No, it's a part of the press.
नीचे है
Yeah. See, also in there, experience can be done there also. Yes. Yes, I
ये मॉस किसका है? प्लीज एक टाइम ठीक है
बस बड़ा
बस नहीं This is tonight, but
So welcome back everyone. I hope you had tea, coffee and juice, everything. So we'll start with our next invited talk session by Professor Mukesh Kumar from IIT Indore. It's my privilege to give a short description about Professor Mukesh Kumar. Dr. Mukesh Kumar is currently a professor in the Department of Electrical Engineering at the Indian Institute of Technology Indore. Received his Masters of Technology MTech from Indian Institute of Technology Kharagpur, India in 2004 and PhD in Electronics in 2009 from the Tokyo Institute of Technology, Japan. He had been in University of California, USA as an exchange researcher. He was a JSPS postdoctoral research fellow in Tokyo Institute of Technology, Japan. His research interests include integrated optoelectronics, silicon photonics, nanophotonics, semiconductor optoelectronics, and nanofabrication technology. He has executed a number of sponsored research projects funded by Government of India and currently working on several research projects, including one under National Quantum Mission. He has published over 100 research articles in journals and conferences of international repute and has published 5 patents. He is also leading the Photonics Outreach Program of IIT Indore to reach out to higher schools and small colleges for spreading the know-how of photonics and semiconductor technology. He has also served as the founding head of Center for Advanced Electronics at IIT Indore. He is also serving as the associate editor of IEEE Photonics Journal. He is the recipient of Scientific High-Level Visiting Fellowship 2023 from French Institute. He is a fellow of Japan Society for Promotion of Science, a senior member of IEEE, and a senior member of Optical Society of America, Optica, and a life fellow of Optical Society of India. He is an adjunct professor at the Cornell University, USA. Sir, I would now request Professor Mukesh Kumar to please take over the session. So please.
So the introduction was little long. I'm sorry for that. So thank you so much, and thanks to Professor Shevan Mukherjee for organizing such a wonderful event in this very beautiful ambience, little away from IIT campus, but still it's good. So I'll be speaking on what we do in our lab, specifically utilizing semiconductor heterojunctions for developing some of the devices for various applications. And the major application of our devices which we work on is in communication basically, and then sensing. So I'll start. I think there are some students also, new students, so I'll be touching upon some of the basics also in between. When it comes to communication, we know that the human civilization has been, growing, and we wanted to connect, and we wanted to somehow preserve those connections, those informations also. So that connection was, or that communication was initially in form of sending signals in form of fire or so, and then we had some other means of communication also, like sending through birds or so. Then this was the breakthrough in communication when Graham Bell tried to connect Boston and Cambridge through his photophone transmitter and receiver. And it was the first time when he used sunbeams to connect for communication. And then slowly we had seen a lot of changes, a lot of developments in that area, starting from the birds and so on, and telephones and so. So these days we use optical fibers. We have optical connectivity where you basically communicate using light, right? And when you say that, you have advantage. The optics has advantage when it comes to for communication. So what you see here, this is the electromagnetic spectrum, and if you communicate at radio waves or even microwave or even millimeter wave, normally your information carrying capacity for any carrier is proportional to the frequency. So the more frequency you have, more bandwidth you will have. Personally. So then people thought, why not using light for communication? And when you use light, and then you should compare it to radio waves or microwave, you have many fold increase in the frequency. That's why you have, it's not large bandwidth, you have enormous bandwidth. Your information carrying capacity for that carrier wave will be really large. That's the benefit here. That's the optical advantage. It offers you enormous bandwidth, right? So now, we know that almost all long distance communication has been through optical fibers. But that is not the only thing now. You have connections, optical connectivity inside a building. Let's say this is a data center. This I have taken from Nokia. So what you see here, this is a typical picture of a data center where you have these red cables which are copper connections, electrical connections. And these yellow things here, they are optical connections. That means you are connecting different racks using optical fibers. So you have optical connectivity in form of these kind of packages there, and you are basically linking servers, storages, or other networking equipment through light. So you have the data transfer with very high bandwidth and with low latency. That's the beauty here. So that's not the end. This picture is from the SICOA. It was a supercomputer developed by IBM. And at that time in 2012, it was number 3 in top 500 list. And it could have 16 petaflop. Petaflop means how many 1,000 trillion floating point operations per second it could do. And it used 1 million optical fiber. And you see here, all these orange things here, they are optical fibers basically. So you have this optical, you can call it your computing and large extent is because of this, optical fiber grid. So it is being used for protein folding study, for weather prediction, for stock market analysis, and for analyzing smart grid. These are some of the applications. And very recently, Intel, I think last year or so, they came up with their chiplet, photonic chiplet. They call it fully integrable optical chiplet for scalable AI. That's being used in data centers and even for AI applications, so for making hardware. And NVIDIA is going to use such technology now in their processors for GPUs also. So what I believe is that light is the enabler of advanced technologies, right? So when you talk of this high performance computing or AI or neuromorphic computing or even quantum computing, what you need improved hardware or new hardware. And one thing is one solution is that you can process and compute with light. That's one. And there are laboratories, industry which are slowly taking up that challenge. They have come through those ultra low loss waveguides, individual devices, then hybrid integration with utilizing different materials, not only silicon but germanium, silicon nitride, some other phase change materials, or 3-5 semiconductors and dielectrics. So you need individual devices, then hybrid integration, then monolithic integration, and slowly people are progressing in this path, and they want to have passive and active devices and then systems which can have optical processing information. So when we talk about this traditional long reach communication, where you may have connected data centers, the distance can be 10 or 500 kilometers, and then you are coming into a data center where your connectivity can be in meters, or maybe across rows inside the racks, inside those telecom racks or data center racks. You may use special laser called vertical cavity surface emitting laser. You can have the advantage from silicon photonics that you replace the copper, right? And slowly your target may be to replace the copper, optical interconnect. I mean, you cannot, of course, replace whole copper. You cannot completely replace electrical interconnect, but to some extent, if you can replace some of the optical interconnect, and can have electrical interconnect and can have optical interconnect there, and the benefit will be again the same. That is also kind of communication on the chip, right? So you can have enormous bandwidth with you, right? So that has been slowly happening, and you have for telecom, you have several products. For data centers, you have these active optical cables, rack to rack, board to board connections. For on-board, you have intra-chip photonic integrated circuit that is recently coming up, and you are targeting, as I said, copper somehow. And when you are having more and more optical connectivity, more and more optical components inserted into your connections there, you have the advantage of data rate, higher data rate or more bandwidth, right? So there is a problem with when your interconnect density rises, right? So you have especially those VLSI interconnects. The copper will be problematic, especially at high frequencies, for high speed operation, for higher metallic interconnect densities. Copper will be limited. So that's why the one alternative is to use optical interconnects. And when you say optical interconnect, you are trying to insert some of the devices into your processors or into your racks. That's what you want to do, right? So there has been this traditional optical fiber optical confinement where your light spot size can be in 3 micron or so, and then you come down to silicon photonics or 3-5 semiconductor photonics, where your light spot size can be in 300 nanometer. So when you further come down, you can have plasmonic confinement, which is maybe 100 nanometer, even 30 nanometer or so. So in that range from the silicon 3.5 semiconductor to plasmonic, you may have several waveguide geometries to make your devices. It may be rich structure, like completely silicon and digital form. You have rich on SOI, you may have the slot, or you may have hybrid plasmonic. So when you are going from here to here, your sensitivity, your dimensions, your geometry becomes more sensitive. You can have really highly sensitive sensors and can have ultra compact devices with these things. So silicon is very good. It is with mature CMOS technology. It gives you very high refractive index contrast when it comes to make photonic devices, but it has problems. For example, you cannot make lasers and LEDs with silicon, and it shows weak electro-optic effect. When you want to have voltage-controlled photonic optical devices with silicon, it shows weak effect. So there are some problems. So you need to have some other semiconductors with which you can make photonic devices, and that's what we call it semiconductor heterogeneous integration, where you want to realize maybe non-silicon or hybrid silicon materials to form devices, to have devices, right? So it may be silicon or 2D material, it may be non-silicon approach, so that you have exotic light matter interactions. There are number of players there already, industrial players who are taking different materials like glass, lithium garbage, polymer, and so on, other semiconductors to make devices, circuits, and systems for various applications. So one category in that hybrid, that heterogeneous semiconductor heterojunction is you have hybrid integration, where you have already fabricated dies or ICs and you hybrid integrate them on a common platform. That's one strategy which people are adopting, and you have solutions, you have products for data centers already, or for computing to some extent. And then you have the kind of what you call heterogeneous integration, which is still going on, where you have in a CMOS, one single CMOS fabrication line, you're also fabricating your photonic devices in parallel with your CMOS processor, so right? So, fine. So in our lab, we are focusing on three divisions here. The one is engineered silicon, where we try to engineer the silicon and then realize some of the devices. There is no other semiconductor used in this division. We are doing that, and we have made some of the passive devices out of this. And then we are into the semiconductor heterojunctions, where we are taking silicon and ITO. We are utilizing ITOs epsilon near zero with silicon, so that we can make some of the optical modulator or photodetectors for telecom application and for sensors. We also sometimes back we started with zinc oxide based devices, which we stopped for some reasons because we don't have the growth facility. We may have deposition in, but so we stopped this. But we had developed optical modulator for visible light communication in that range. And then we are also into nanophotonics, where we are utilizing hybrid plasmonic devices for some applications. I'll tell you that. So for engineered silicon, we start with this. This is a kind of an optical filter on SOI. The top silicon we have engineered it. This is one comb. This is another comb structure on this silicon, and we have inserted a cavity here. Because of this cavity, your two peaks will overlap, and you have overlapping kind of band rejection windows which are sensitive to any change. So you can have filtering operation. You can use it for sensing because it is sensitive to any change. You put some light, this overlapped region will shift. So this shifting will be the signature of any analyte, presence of any analyte. That's what it is. So we have fabricated this. And when you have silicon, let's say you have this rib structure of silicon, and this may be in your 300 nanometer thick and maybe 200 nanometer wide, and you have very strong optical confinement, very simple rib waveguide, which can very nicely guide the light. what you do here intentionally, what we did, we thin down the silicon. So that light leaks vertically up. So it leaks. It's not of use, but what we do, do that you have another semiconductor. You have thinned down the silicon, and then you have another semiconductor deposited over this. You call it X. This can be anything, any other semiconductor. So now you can utilize the properties of this X, whatever properties it gives you, and you have what you call it silicon X hybrid waveguide. For example, in our case, this can be ITU, utilizing epsilon near zero, very low permittivity of ITU, so that it gives you large index change, large tuning range. So another thing which you can do is you try to engineer this silicon where you form this grating kind of structure from using our lithography and then wet etching process. We created this trench over the silicon. So what you do, you have this silicon and air, then you fill your X semiconductor here. So this X can be best in class semiconductor. So you can mold the flow of light which is propagating here, and you may have semiconductor heterojunctions which are multiple distributed along the propagation of the light, right? So we started using ITU, and in our lab we have this deposition system where we play with the oxygen partial pressure and we try to vary the carrier concentration there, and then realize very low epsilon. It's not zero, but it is very low. If your epsilon is very low, you may have large change in refractive index, so which may tune the light, which may control the properties of output light. That's what we do. So we inserted it in a very simple structure. You have this silicon gray color waveguide that is thinned down intensely, and then you deposited our engineered ITU over there. So whatever optical mode is confined, it will see the ITU also. So when you apply voltage over ITU, its refractive index will change, so the light output will change. So we try to modulate the light, and the good thing is that you can modulate the phase of the light as well as intensity of the light. You can make phase modulator and intensity modulator. So we fabricated it in our lab and tested it, and we could have 7 dB X incineration, which was not that good, but still we were happy that it was a starting process. Then one problem with integrated photonics is that when your signal is coming from the optical fiber and you want to graze it on the chip, then you have loss here. From the optical fiber to the chip, you have losses. Or from the chip to the optical fiber, output fiber, you have another losses. So you have to have external or extra couplers, input coupler and output coupler. So you usually use separate grating based coupler which will take in the light from the fiber and will nicely propagate it to your device, which is in plane. So that is another headache. So what we were thinking, can't we make our device, design our device such that your coupler is an integral part of this and it still shows the same device behavior which you expect of. So we did that. As I mentioned a few slides back, that we had this distributed heterojunctions and a grating. It's playing a double role here. So it is acting as an input coupler, output coupler, as well as it is enhancing the light matter interaction because of this P-type silicon and N-type ITO, these distributed heterojunctions which are distributed along the length. So we did some simulation, try to understand what is happening, especially when it comes to light matter interaction, and then we fabricated it in our lab. Then what we did, we tested it initially. We tested what happens when you are shining the light from the fiber to the chip. What happens when you vary the angle of the fiber incidence. So from 0 degrees to 10 degrees, you have certain degrees in the transmission, optical transmission, but it is still acceptable. Then we went ahead, we tested its modulation characteristics. When you apply voltage from 0 to 5 volts, so your optical transmission peak also shifts. So we had 24 dB separation between optical on and optical off. That means it's a kind of switch. It's a kind of intensity modulator, which is modulating the output intensity. So similarly, with the same technology, we extended it to ring resonator. Ring resonator, very versatile optical component, the optical device where light resonates in this ring. So because of this resonance, we have this resonance signature, we have a dip in the output spectra. So now this shift, because we are using IQ here, when you apply voltage, this shift will also, this peak will shift. So you still call it modulation. We are able to, control this shifting by varying the applied voltage. Now, the similar concept we utilize for a control NOT gate, which is a silicon photonic control NOT gate. It is not quantum, it is classical, but we can enable it. So the signal in this waveguide can control the signal here. We have three switches here, three previous switches which we fabricated and tested before. So we used those three switches here, and we could realize almost propagation of 0.02 dB per micron, and the extinction ratio was 10 dB for this kind of switch. So whenever your control signal is 2 more minutes, okay. I think I'll be able to finish. Okay, so then similar semiconductor intersection technology we are utilizing for biosensors, especially to have optoelectronic sensor to detect lung cancer. So what we do here, we utilize this TiO2 and zinc oxide kind of device, which is a kind of photodetector, and when you put analyte there, your lung cancer cell on it, then your photocurrent drastically increases. So this is the signature of the presence of lung cancer. So we are still working on it. So then in our this nanophotonics, basically utilizing hybrid plasmonic behavior, what we have here, we have this silicon there, and on top of this you have SiO2, and then this is thermally oxidized SiO2, and then you have gold. So what happens basically, your light in form of light and plasmonic confinement, because of the gold and dielectric presence there, you have combination of SPP, plasmonic confinement, as well as light. So what do you do here? Because they have metal, dielectric, and hybrids or silicon. So when you apply voltage over it, it has a signature of memristive effect kind of thing, right? So it's a resistor switch which we are trying to read optically. So once you shine the light and you are varying the voltage, you may have these conducting filaments, metallic filaments, maybe more or less. They can be more, they can be less. And when you shine the light, they can absorb the light in a larger amount or with a smaller amount. So you can have optically on and optically off. The problem was, can you design your device so that these optically on and optical off can be separated enough so that you can really call them on and off. So we could do that, and initially we had 10 dB of extinction ratio, and then we also have utilized another geometry, and we could realize, I think, few tens of dB of the extinction ratio there. Similar device, we could have multiple nanophotonic resistance switches where you have this high optical intensity, moderately high, moderately low, and low optical intensity. We have multi-level optical reading there. So then we, based on the similar concept of this nanophotonic, what you call it, nanophotonic resistor switch, we had developed a multi-wavelength nanophotonic circuit, which is reconfigured. You can reconfigure it, and it is a multi-channel. So you can switch on and switch off any of these 8 channels at your wish. So you call it reconfigurable thing. And now we are extending it for a chip scale programmable circuit. It's a kind of programmable photonic integrated circuit where we want to have efficient electro-optic reconfiguration. And we want to utilize semiconductor heterojunctions for it, and silicon ITO may play a role here. So we have initial results for confidentiality. I'll not be able to show these results now, and for the shortage of time also. So to summarize, semiconductor heterojunctions are good for heterogeneous integration. You may have hybrid engineered silicon, so that you have exotic electronic and photonic characteristics, and you may look at next generation photonic integrated circuits. You can have hybrid plasmonics for sub-wavelength optical confinement, for example, for to read resistor switch optically, and we are still exploring some new applications of those nanophotonic resistor switch. And this is my team. We have a lot of people, not a lot, but good amount of people who are, working really hard to contribute within our limitations. So we are funding from DST, recently from National Quantum Mission, and we have very kind and strong collaborations. And thank you so much. If there is any question, I'll be happy to answer that.
We can take only one question due to shortage of time. So participants and attendees, anyone has any question? Okay, so we have no question.
Please. Yeah, okay, thank you.
This Q value for 2000 can be achieved. So what is the expected Q value?
Which one?
Q value.
Q value. Okay.
Very high.
Very high. Actually, in our application, although for some devices, some optical devices, the Q value can go to 10⁻⁶ or so. There are some results. But if your Q is very high, then it is very difficult to extract the light out from there. So we wanted to intentionally keep the Q at thousands, few thousands. So, but we can go till 10⁻, I think 4 or 5. We want to calculate.
Thank you so much.
Thank you so much.
Thank you, sir. I would now like to invite Professor Seval Mukherjee to present a memento. Professor Mukesh Kumar is a token of appreciation and gratitude. Thank you, Professor Mukherjee. Thank you, Professor Kumar. On behalf of the IEEE community, I take the opportunity to thank our speaker, Professor Mukesh Kumar, for this valuable time he took to share his expertise with our community. Now, moving forward to our next invited session by Professor Ramvilas Pachauri, Professor and HAG and Institute Chair Professor at IIT Indore. I would like to give a short description about Professor Ramvilas Pachauri, sir. Professor Ramvilas Pachauri received his B.Tech in Engineering degree with honors in Electronics and Communication Engineering from Rajiv Gandhi Vishwavidyalaya, Bhopal in 2001, and then he's in Electrical Engineering from IIT Kanpur, India in 2003 and 2008 respectively. He is currently Institute Chair Professor in the Department of Electrical Engineering at IIT Indore, where he has been Professor since 2020. Earlier, he was Professor, Associate Professor, and Assistant Professor at the Department of Electrical Engineering, IIT Indore, Assistant Professor at International Institute of Information Technology, Hyderabad, India, from 2008 to 2009. Postdoctoral Fellow at Charles Darwin University of Technology of Troyes, France from 2007 to 2008. He is Fellow of Institute of Electrical and Electronics Engineer, that is IEEE, Indian National Academy of Engineering, that IIT, and Institute of Engineering and Technology, Asia Pacific Artificial Intelligence Institution of Engineers, India. He is IEEE EMBS Distinguished lecturer and academic mentor for Leadership Academy. He was associate editor of IEEE Transactions on Neural Systems and Rehabilitation Engineering from 2021 to 2024 and IEEE Open Journal of Engineering in Medicine and Biology from 2024 to 2026. Currently, he is associate editor of Electronics Letters, Computers and Electrical Engineering and Biomedical Signal Processing and Control. He is also serving as deputy editor-in-chief of IEEE Journal of Research and the editor of Signal Processing and editor of IEEE Technical Review Journal. Now I would like to invite Professor Ramchalas Kachori to please take over. So please.
Yeah, thank you very much for nice introduction, and thank you for the opportunity to be part of this conference and to deliver the talk. Thank you. So, topic of this talk is intelligent systems for EEG-based epilepsy detection. So, in this talk, we will see actually recently our group has developed intelligent systems based on signal processing machine learning for automated detection of epilepsies using EEG signals. So, that will be discussed in this talk. And there is a lot of use of such kind of systems.
So you can.
Like in rural areas where you have shortage of doctors, and such kind of systems can help actually the patients to detect the disease early stage, so timely treatment can be carried out. In urban areas, we have more number of patients, less number of doctors. So such kind of systems actually can help doctors to perform efficient diagnosis. So there are a lot of applications. So with this background, let us start this talk. So this is the overview of this presentation. First, we will see introduction and then motivation for this kind of intelligent systems, which are based on multi-channel signal processing. And then empirical mode decomposition. So the signal processing actually used to work in different ways, different principles. But here in 1997, this new way of signal processing came. And that's such one example is EMD that will be explained. And after that, we will see empirical wavelet transform that is actually motivated by the EMD limitations. And then this our group has proposed multivariate empirical wavelet transform that will be explained in the, and then after that you will see its application for detection of epilepsy from EEG signals. And in the end, conclusion will be provided. So this actually one of the fundamental problem in actually biomedical signal processing. We have signals, and these signals they have a lot of information, and how to extract such kind of information. So for that, actually, we represent these unknown signals, biomedical signals, in terms of non-functions. And Fourier, actually, 1807, he suggested use of sinusoidal functions to represent the unknown signals. And so if you use this Fourier transform, then there are different kind of signals. And one kind of actually classification is staging non-staging signal. And if you apply this Fourier transform for staging non-staging signals, then actually this spectrum is not, it is coming out to be unique. So this is staging signal and that is non-staging signal. And the spectrum is actually same. So this is one of the major limitations of the Fourier transform. So motivated by that, there has been two directions in the literature. One direction is actually fixed basis. So here we design basis functions from our side and we represent unknown signals in terms of such functions. And other one is adaptive basis functions. Here actually we develop algorithms, and these algorithms obtain such kind of functions from the signal. And such examples include empirical mode decomposition, empirical mode transform, etc. And here in both actually directions, what we want to have such kind of basis functions which can give unique spectrum representation for staging signal, non-staging signals. The whatever representation we are using, that should be unique. So based on that motivation, such kind of signals have been proposed in the literature, like time varying and time varying frequency. So they are the general form of the cosine sinusoidal functions. And this model, when we are using these actually signals in terms of summation of such kind of time varying sinusoids, then it is suitable for univariate signals, and they are multi like frequency, so wideband data. And now actually the recent trend in the signal processing actually is going towards multi-channel signal processing. So this model can be this one such model, exactly this model, both can be used to generate this or to define multivariate signal. So this is actually multi-channel signal where each signal is narrowband, and this is multi-channel signal where each signal is wideband. So this model, this mathematical model of multi-channel signal processing will be the foundation for this talk. And there are many scenarios in real life where we have multi-channel data, and three such scenarios you can see in this slide. First one is gear for diagnosis. So where we use vibration data, which is recorded using here two sensors. Other application is EEG data recording, where we are using electrode tab. And number of channels in the tab determine the number of EEG signals in multi-channel data. And third one is ECG recording. So here we are putting actually leads on the chest. So number of leads determine the number of channels in the multi-channel data. So in this all these scenario, if you are actually processing this data, if channel wise individually, then you are ignoring the correlation between the channels and also the mutual information between the channels. So, and there is other reason also, like the previous slide you might have seen, this adaptive signal decomposition approach, data-driven techniques, where we have actually algorithms kind of concept for decompose the data. When you apply to individual channel, then actually since they are data dependent, so each channel will give you different number of components. So each channel will have different components. So mode alignment property will not be present. So this is problematic for my medical applications. So like one channel can have, for example, 5 components, other channel can have 10. So how to compare 5 with 10? So this is a problematic issue. So motivated by that, this actually multi-channel signal processing is forcefully you have to actually follow. Then only each channel will have same number of components. So these three reasons, major three reasons that actually motivates to apply signal processing in multi-channel data. And there is now new direction of research is coming in signal processing, in multi-channel signal processing based intelligent systems for healthcare applications. So this was actually direction. This was the breakthrough in this signal processing. Earlier, 1997, people used to design basis functions from their side, and these unknown functions, unknown signals were represented in terms of the known functions. They were man-made functions. But 1997, Hilbert Wang actually they come up with some kind of concept. So you don't need to design basis function from your side. On the other hand, you will use such algorithm to extract these components from the data. So this is just like empirical mode decomposition. You don't need to assume any conditions about the stationarity, non-linearity, whatever data is coming, you just give in this form of the algorithm, it will decompose it. So this is just a brief overview of this algorithm. So we have a signal and determine the maximum, minimum, and extremas. That based on that we interpolate both of them. Then we get the two envelopes. One is corresponding maxima, other one is corresponding minimum. And that average of these two envelopes is actually subtracted from the signal that we have residual. And residual, that forcefully we want to have like amplitude and frequency modulator, like the time varying sinusoids. So it should satisfy two basic conditions of the intrinsic mode function that we call, and that is number of zero crossings and number of extremas. This should be different at most by 1. So this condition ensure that whatever IMF you get, that is actually like sine to sine function. Second condition ensure that like this average value of this residual is 0. So this ensure that whatever residual you have, that like symmetric. So based on these two conditions, so whatever IMF you obtain, we assume that they are symmetric sinusoidal, time varying sinusoidal functions. And this once you get the first IMF, then you subtract this IMF from the signal, then you get new residual and repeat the same process. So in that way, we get all possible IMFs from the data. And Professor Patrick Pleanry and his team, they have shown that whatever these components you have obtained using empirical mode decomposition approach, they're similar to a wavelet decomposition kind of it. So indirectly, without designing mother wavelets, without knowing number of levels, you can actually have decomposed components, and they represent different scales. So first IMF, that is the highest frequency component of the data, and which is the lowest scale, that is actually detail. And last one, 8th IMF, that is the highest scale and lowest frequency, that is called approximation. So similar to wavelet kind of decomposition, it can be obtained. So that is multi-resolution analysis kind of approach. And there is a lot of work has been done in direction. Various multivariate concepts have been proposed: complex EMD, rotation invariant complex EMD, bivariate EMD, multivariate EMD, fast EMD. And this EMD actually has got two major limitations. Number one limitation is actually the empirical in nature, and people they are struggling to understand how it works. And the second one, that is actually it has mode mixing problem. So each IMF, intrinsic mode function, is expected to be like one mono component amplitude and frequency modulated sinusoid, but due to this decomposition process, sometimes it is mixture of both. So motivated by that, this new signal processing technique, empirical wavelet transform, was proposed in the literature, and we have extended this for multivariate empirical wavelet transform, and then we have applied its application for epileptic tests. So epilepsy, that is actually one of the serious neurological disorder, and EEG signals are commonly used for diagnosis of epilepsy. And in brain, all neurons they synchronize together and generate very high electrical activity. And that actually, due to that, when you have high electrical activity, then brain disturbs. And brain is the master of the body. Once brain is disturbed, then everything is disturbed. So that actually is very serious disorder. It affects around 2% population of the world. And we have proposed this empirical wavelet transform based approach for patient-specific epilepsy detection. So here you can see this is the human brain. It has 4 major lobes: temporal, frontal, parietal, occipital. So whatever you do directly, indirectly, everything is actually associated, or everything is affecting one of the regions. So EEG signal is so powerful signal, like whatever happens in the body, effect can be seen in one of the regions. And to get the electrical activity from one of the regions, we use electrode cap. So electrodes are arranged in such a manner that it can record activity from any of the region, any of the places from the ground. And just for an example, 2-channel EEG signal is shown. But it depends on the application number of channels in the electrode cap, and then it can have 128 EG also, 128 channel data, 64 channel, depends on the application. So already we have seen motivation for empirical wavelet transform. It comes from the limitation of the EMT method, and it has 3 main steps. First one, empirical wavelet transform, 3 steps. First, it comes to the Fourier spectrum. And then you segment the Fourier spectrum into different regions, and each region is corresponding to mono component. And from that, actually, we define empirical wavelets, and we use them as a band pass filter. And these components are separated. So our contributions include extension of this empirical wavelet transform method for multivariate signals, and then we have suggested time frequency representation of multivariate signals using the CWT with application to epileptic seizure detection. So now you have this, for example, multi-channel data, and if you apply EWT method, empirical wavelet transform, to individually, then actually each channel will have different Fourier spectrum. As a result, it will have different boundaries. So due to that, it will have different number of IMF components. So this mode alignment property is not present. So what we have suggested, we take the average spectrum, which is computed from the spectrum of each channel, and that average spectrum will be used to define the actually boundaries, and whatever boundaries from that will design the empirical filters that can be used for individual channel, so that each channel will have same number of IMFs. So mode alignment properties are there. Then we have actually suggested use of Hilbert transform to each IMF, so that steadiness and different frequency are computed. And then actually this mathematical framework we have proposed to compute the multivariate time frequency representation. So this time frequency representation is actually takes care of all frequencies present in the each channel and all channels. So this is more general form of the time frequency representation. And then actually, this is our proposed epileptic seizure detection system. And this for study purpose, we have taken this VisionNet CNP MIT scale V data, one of the actually benchmark database for this kind of study, which has EEG signal from 23 patients and 23 channels. So if you use all 23 channels for study, then actually the proposed method will suffer from huge computational complexity. So what we have suggested out of 23 channels, actually we have selected 5 channels, and this first channel with visual deviation, and other 4 channels based on the relatively higher visual information with the first second selected channel. So this epilepsy is like a short temper. We call this person is short temper. This means he becomes angry and after that quickly he becomes relaxed. So similarly, epilepsy is also has that actually feature. It comes for a very small interval of time and after it becomes normal. So that's why we have selected standard deviation. If it is standard deviation is higher, this may be due to noise. So these actually, based on these 2 criteria, we have selected 5 channels. And then we apply empirical wavelength transform for this 5 channel EEG data. And then each channel is given 10 modes. And then we compute distance, amplitude, and frequency of each mode using Hilbert transform. Then joint distance, amplitude, and frequency of each mode is computed. And then we have feature extracted from different modes. And since it is surface EEG data recording, so it suffers from noise. So some feature processing is also needed for the making the features well behaved in order to use it as a diagnostic features. And then we have used machine learning based classifier, which will actually classify automatic seizure and seizure real classes. So this kind of frameworks are very useful. In many countries like South Korea, people actually wear such kind of frameworks in the form of wearable devices. And suppose somebody died in a car and a person is going to have epilepsy, then actually this kind of device framework will generate the alarm. And the person will stop the car and take the epilepsy drugs, and then actually can bypass. So it's very useful techniques. And this is very interesting result. This is 5 channel EEG data and during seizure, epilepsy. And this is actually 5 channel seizure free data. So you can see when you propose time frequency that we have proposed, it has all kind of frequency component present in this actual time frequency plan. On the other hand, in the seizure-free case, you have only low frequency component. So this can be used as a signature for computer-aided medical diagnosis. Even without doctors, person can actually detect that he has all frequencies in this plane. This means person has epilepsy. So that actually detection of the disease can be done in rural areas without presence of the doctors. And then actually you can go to urban areas for timely treatment. And then these are the features from the all modes, all frequency components from all channels. And then these are the noisy. So what we have suggested, moving average filters, and then actually denoising is done. So these are enhanced features. And then you see this in the middle, that is higher. And that is actually presence of epilepsy attack. So if you multiply higher with higher, what will become higher? And lower, multiply with lower, it will become lower. So based on that actually concept, we have suggested Hadamard product. And when you multiply all of them, then actually it becomes higher. So this is actually beauty of the signal processing. So now here see this is raw EEG data which neurologists actually use for the diagnosis. Like when you go to hospital, doctors actually use this signal. They do visual inspection of this kind of signals, EEG signals, and you can see that there is no indication where the epilepsy attack is happening. But if you see the process features, it nicely shows that actually epilepsy can be detected with these features. So the signal processing can help you to find out the actually initiation of the epilepsy attack, and when it becomes severe, when it is becoming down, onset, offset, all kind of information signal processing can give you. So that actually this kind of features the researchers use to predict the epilepsy. So that is actually epilepsy is considered like earthquake in the brain, and around 5 to 10 minutes before such kind of systems, this kind of actually features become very low at that, and here it is clearly severe. So this time actually gives us an opportunity to define such kind of systems which can predict the epilepsy. So based on that, actually can predict epilepsy, and then we have given these as an input to machine learning classifier. And then many actually the literature, many researchers have used signal processing machine learning techniques. In this table, you will find many such methods. And some groups use all channels, some groups only they have taken only 5, but how to get 5, that's not clear. 23, 6, out of 21, 80 channels. So our method we have used out of 25. So 3 features actually obtained from the reference oscillation labels using multivariate XOVWT. And based on 10-fold cross validation, it gives you a specificity of 99.57%, sensitivity 97.91%, accuracy 99.4%. So whenever you have epilepsy, you go to hospital, doctors generally see 2 features. So they see the presence of spikes in the EEG data and large and bigger EEG data. So both actually indirectly, whatever features we have proposed, we have actually translated the clinical knowledge into engineering features. And then this is the conclusion of this talk. So proposed multivariate empirical wavelet transform is able to decompose multi-channel, multivariate signal into meaningful components. So in that way, actually, this is one application where we have proposed intermediate systems based on multi-channel signal processing, but they can be also extended for other applications. And mode alignment is the most important property of multivariate decomposition technique. Proposed method properly align the similar oscillatory components across different channels. And the proposed method has provided good detection for epilepsy diagnosis based on scalability. So this is scalp actually, there are 2 kinds of epilepsy. One is generalized epilepsy, second one is focal epilepsy. So for the generalized seizures epilepsy, we actually scalp EEG signals we record, and sometimes they are noisy. So our signal processing technique is so actually good that actually that can handle the noisy EEG signals also. So the selection of the spoon depends on the type of food. So if you go to a restaurant and sometimes you are having noodles, then you fall because your food is discontinuous, spoon is also discontinuous. So similarly, a signal analysis technique, whatever we have studied, that is also actually similar to the signal that you want to analyze. So they are nicely matching with the requirement. And so focal epilepsy, focal EEG, actually that intracranial EEG signals needs to be recorded. They will record from inside of the brain. And they are not noisy. So for them, actually, we have also done work in that direction, but that is not included here. The proposed automated technique can be used for assisting neurologists in their decision making. And the computers, smartphones with the proposed algorithm can be used for the diagnosis of epilepsy in the areas where we have shortage of doctors. Generally, when you have a smartphone, then people think we are smart. But if a smartphone is doing smart work, then you are really smart. So if your smartphone can detect the disease in initial state, then everybody will say you are smart. So actually what algorithm, whatever you have proposed, we are integrating a smartphone. So everybody will be smart in terms of taking care of the health. So this talk is based on this reference. I request all the participants in order to have more information about the presented work. Please go through this application. Thank you very much.
We can take a couple of more questions, like we can take a couple of questions. I would request the attending participants to ask their please to the same speed.
Actually, when we record this biomedical signals, actually, like EEG signals, this noise is spark effects. The noise is like what the noise we have in other signals. So that actually it is not high frequency noise. It is like artifacts. They are interfering with the actual signals. So that is. Yeah. So people use ICA, independent component analysis, branch or separation to separate these articles. So here actually we have not used any pre-processing or because our signal decomposition technique itself can take care of. Because that itself is doing this teacher extraction, decomposition, low frequency, high frequency. Other groups they use independent component analysis, ICA, bands of separation to filter out the artifacts that we call noise. So it may be electromyogram, EMG, other biomedical sorry, eye movement. Yes. Yeah, that is what actually. So it is based on the neurologist validation. This high when you have epilepsy, when you have spikes in the age data, so there is a presence of high frequency components, and you have large amplitude. Because all neurons they synchronize together, generate very high amplitude. And in case of schizophrenia, this is very low. So if you see rural areas, actually when you have epilepsy, what people do, they ask that person to smell very old socks, old bananas. So that is the due to that smell, neurons will be busy in other side. What? So this electrical activity will come. So that person will go to God. So this neurological actually study has shown that in epileptic case we have high frequency components. In schizophrenia, there is not. And so based on that we work with.
Any more questions from the audience?
Rural areas, people use lot of actually radio research. When they have epilepsy, they know the reason. Yes, I'm sure. So old bananas, and I mentioned this in Italy, and they say how to bring old bananas. Because people they have only fresh bananas. Villages you will find old bananas. That is actually what sometimes old bananas are also featured for the epilepsy.
This you mentioned something ECG also, right? So
Yeah. So this is for brain diseases. But ECG, this is these signals will be recorded from the heart.
you are doing something with ECG also.
Yeah. So this whatever method this is for neurological disorders. Same kind of method we are also doing for ECG and vibration also. Wherever you have multi-channel data, such kind of methods can go. Yeah, single channel and multi. Sometimes you don't have multi-channel. So sometimes you have one lead ECG, and so like there is multi-modal concept. So we use like Ieee ECG together. So EEG may be multi-channel, ECG may be only one. So the hybrid approach can be used. So that's it. So computational complexity little bit it will increase because we are taking all channels together, but on the cost of computational complexity, live electricity is.
Thank you, sir, for such an informative session. I will now as a on behalf of the Icitsif community, gratitude to Professor Ramvilas Pachauri for taking out his time and efforts to share his expertise with us. Moving on to our next invited talk session by Dr. Rohit Singh, Assistant Professor, Pleanry University. I would like to give a short introduction about Dr. Rohit Singh. Dr. Rohit Singh received his BTech degree in Electronics and Communication Engineering from Uttar Pradesh Technical University, Lahore, India in 2012. followed by an MTech degree in electronics and communication engineering from Shivnatha University in 2014. He earned his PhD degree from the Electrical Engineering Department at IIT Indore in 2018. He is currently serving as an assistant professor in the Department of Chemical Engineering at Shivnatha University since April 2020. His research interests include nanoelectronics, Internet of Things, and embedded systems with a strong emphasis on practical and application-oriented learning. I would request Dr. Rohit Singh to please take over the stage and continue with the talk. Sir, please.
So I will present one of my work which is used to extend the battery life of IoT devices. So basically nowadays we design many IoT devices using microcontroller development boards like Arduino boards or STM32 microcontroller boards or Silicon Labs boards where you integrate the sensors, actuators and the transmissible module, and these basically runs on battery. So if we implant those devices to let's say monitor the indoor environment like air quality, different parameters, and we want the data after every 30 minutes. So the data collection will take hardly 1 minute, and rest of the time the microcontroller will be still running and consuming power. So the battery will be drained even if you connect a battery of 1000 milliampere per hour, 1000 mAh battery drained in 4 to 5 days. So how to extend the battery life without compromising the functionality? So I have developed a device. So we'll go with the motivation. Different approaches for power saving in the IoT sensor node, and then what is my proposed system, and design a power controller unit, prototype results, and submit. So motivation is only how to extend the battery life. So the traditional approach to extend the battery life is that you put the microcontroller into sleep mode and then wake up it. But there are certain problems with the sleep mechanisms. Like sometimes if you put the microcontroller into deep sleep mode, it will not wake up. It will require an external interrupt. So external interrupt is always a manual trigger is there and it will create a problem. Also sometimes you have to make certain changes in the hardware itself to do it. Okay. So even if it is in the sleep mode, the development boards continuously consume currents. Those currents are generally in the range of 20 milliampere to 30 milliampere, but that current is also very large for like it will even drain the battery for 5 days. So these are the different approaches to save the power. Like you can choose the low power microcontroller, which will basically consume less power or less amount of current to complete your task. Okay. You can use the energy efficient sensor. So while purchasing the sensor, just check like what is the power consumption of that sensor. It should consume very minimal power in the standby. Because most of the time the sensor is in the standby, so we have to choose a sensor which will consume very less power in the standby mode. We can also integrate the energy harvesting things with the sensor node so that the battery life can be improved. And we can use the efficient power management systems to improve the again to increase the battery life. So those are the things which you can do at the hardware level. Certain things we can do at the software level also for improving the power or like power optimization. So at the software level we can use the lightweight operating systems for controlling the different applications which are running at the microcontroller. Like we can use the tiny OS and the 3 or if you are running the multiple programs simultaneously at the control. Then instead of going into the continuous polling kind of programming, we can do the interrupt driven programming so that the power will be consumed at the interrupt time. Energy profiling, so we can continuously measure the energy, etc. And duty cycling is the same like sleep awake mechanism. Now in the sleep awake, instead of going to the periodic, we can go with the dynamic sleep awake. So dynamic sleep awake is something like we are monitoring certain parameters. We can check the previous value and then we can adjust the next sleep time. So that the sleep time is not fixed. So how we can exit from the sleep mechanism? Like exit from the sleep mechanism. So I have designed a separate power controller unit which will power up this main sensor node whenever required, and then it will turn off the power supply of this main sensor node. So this sensor node will like measure the sensor data and then transmit the sensor data wirelessly to some location, and after that it will send an acknowledgement signal to the power controller unit, and this unit will cut the power supply of this microcontroller. So we have to design a power controller which should basically run at the minimal current. So our aim is that if we are able to run this PCU at the 5 milliampere at the 1 milliampere, then it is very good, and it will extend the battery life by 5x or 10x. So I have designed this power controller unit with the help of these four components. This is the main brain of this power controller unit, which is 80 tiny 1660 microcontroller. So this microcontroller basically consumes 10 milliampere current when it is running at the full load. And then this is another real-time clock module which will keep track of the timing things. So you can program this 80 tiny to turn on the power supply either periodic, like you can fix the time period, or you can fix the like at particular time instant you can measure the power. So all those things we can program it here. And then these are the two voltage regulator IC. So this is this two of the low drop of voltage regulator IC. This regulator IC is giving 5-volt output, and this is used for driving this microcontroller and this RPC module. This is another voltage regulator IC which is giving output current of 300 milliampere at the 5 volt. So this will have a enable switch. So this enable switch will be controlled by this microcontroller. So whenever enable switch is on, then this will deliver the power to this main microcontroller. So this is the 3D module of the developed prototype. So we have also fabricated it, the PCB and every component we have tested it in the lab. So this is our actual board which we have developed. So for testing this board functionality, we have used an Arduino board, connected a LoRa sealed over it as a transceiver, and connected a DHT11 temperature sensor for sensing the parameter. So this temperature sensor is collecting the sensor and temperature and humidity data and send it to the microcontroller, and the microcontroller have a LoRa module which will, with the help of LoRa, it will transmit the data wirelessly to some remote locations. Now at the remote locations, we have another LoRa module to receive the data and display it. So we are giving the power supply with the battery to this our developed module, and this will periodically turn it on and off. So for completion, we have taken the different cases to see like how much power we have saved. So if we run the sensor node bare minimum code, like if we run the Arduino board at the bare minimum code means let's say there is no code. Just run the microcontroller and test like how much current it is consuming. So Arduino board will consume minimum 27.5 milliampere current if there is no load is running. Now if you turn on the CPU, the PC power controller unit which we have designed at the bare minimum code, so it will consume 50 milliampere current. Now when we connect the sensors and transceivers with the Arduino, so sensor node sits in the ideal mode without using PCU. So if let's say the power controller module is not connected with the Arduino board, and then Arduino board is connected with the sensors and transceiver, but it is not measuring the sensor data. Then in that case, this Arduino board is consuming 30 milliampere current, and if we connect PCU, it will consume 50 milliampere because the PCU cuts the power supply of the Arduino. Then if you are active mode means we are collecting the data from the sensor and transmitting to the using the LoRa module. In that case, it is consuming 61.5 milliampere current, and with PCU we are consuming 47.5 milliampere current. So this active time is the time when like actually the sensor data are collected and transmitted. So this time is basically very small. If you take a 24-hour scenario and if you are collecting data at let's say 10 times. So data collection one time will let's say consume 1 minute, So the sensor node will be an active mode for 10 minutes only, for 10 times data release. Rest of the time it will be in the off mode, so at that time it will consuming only the 50 milliampere current. So with that, like we can here if you see it is like just Arduino is consuming 30 milliampere. With PC we are able to save the 50 milliampere extra. So with this we can generally save the battery life. So we can increase the battery life by 2 years. Now at this increment I have not applied any kind of software optimization at the PC at 8090 microcontroller. If we optimize the 8090 microcontroller further, like the low power modes are reducing the clock supply and putting it in the deep sleep mode for the periodic data collections and waking up with the help of the watchdog timers which are running internally in the 8090 microcontroller, then that can go up to this 50 milliampere can reduce up to 5 milliampere. So if we reduce up to the 5 milliampere, then basically we will increase the battery life from 2x to you can say like 5x. Now these are the like major culprit when we are designing a low power sensor mode. The first major culprit is the LED. Sometimes we put the LED without knowing that okay LED is just an indicator. But LED will consume continuously 10 milliampere current for lighting. Now if you connect a 1000 milliampere, 10,000 mAh battery, so this LED will drain the battery in 41 days. So LED is a major culprit for the low power sensor. So we have to avoid the LED whenever we are designing the low power sensor. Next major culprit is the normal voltage regulator IC which we use 7805. Generally we use this voltage regulator IC to give a regulated 5 volt supply and we connect a 12 volt battery to it. But this voltage regulator IC also consumes 10 milliampere current continuously. So if you connect a LED and if you connect a voltage regulator IC, these are the basic requirements, then your battery will be drained in 20 days approximately with these two components only, not with the microcontroller or the sensor box. And another is the USB to serial connected. These are generally present, which are used to communicate with the laptops and the desktop computers. So these are also consuming 5 milliampere current continuously. So these three components will consume, let's say consume 50 milliampere. So we have to optimize on these components for designing a low power sensor. So if you see my actual design, so here this microcontroller can go and run at 1 milliampere current by reducing by cutting the clock supply to the certain peripherals which we are not using inside the controller. But I cannot do much with this voltage regulator IC because this voltage regulator IC will consume 3.5 milliampere current continuously. This another voltage regulator IC is consuming 1 microampere current to 5 microampere current, so this is negligible. But the output driving capacity of this low dropout voltage regulator IC is that this can support only 10 milliampere output current. So with this you can run this 8010 and other stuff, but you cannot run the Arduino or the STM boards because those require high current. So you require another regulator IC which has to support high current. So it supports up to 300 milliampere load current. But then for its internal operations it will consume 3.5 milliampere current. So we have to think on like whether any other low dropout voltage regulator IC present in the market which consumes less continuous current and give high current output. So that's why I'm saying that maximum we can optimize it to 5 milliampere. So with this proposed system, like I can increase the battery life initially 2x, but in the next versions, like we are planning to incorporate those software optimizations and then we can go up to 5x. So this model I am like collaborating with some of the companies in the Greater Noida. Actually, implant these models in their devices. So I have collaborated with Silicon Labs, which is a multinational company in Hyderabad. So they are interested in this device to incorporate in their IoT products. And also have collaborated with the HBR Labs in the Greater Noida. It's a consumer electronics company which is designing consumer electronic goods. So they are also interested to take this device and put in their things to increase the battery life. So thank you. Any questions?
Sir, for such an informative session, now the participants and attendees can ask their queries.
Thank you, Professor. I'm very grateful to see your.
Thank you, Professor. I'm very grateful to see your presentations and I very appreciate it. I had one questions based on research. Once about obsolete some things from the microcontrollers, LED and LED and some switches on obsolete from microcontrollers. So why we are basically using the LED in the microcontrollers to sense the particular things. So what can be the other thing we can use apart from the LED? Because LED also having a same work in this particular microcontroller to show something. So okay, is there any other component we can
So
use?
like
Instead of LED,
like any other display devices you connect that will consume power. So what we can do, like we can turn on the display devices when it is required. If it is not required, we should turn it off. Like if you see your smartwatches, if you see only then the lights will off. Otherwise it will off. So similarly also we have to think on some mechanism so that when it is required then we should turn on the display devices, otherwise we keep off. In general, what is the practice that we always keep the display devices on. Like you see the Arduino boards and the other boards, the power on LED is continuously on. So we should, like if you are designing our own, so we have to connect display devices for the user interface. But those display devices, like we have to put some sensing mechanism so that it should turn on when it is required, otherwise it should go turn on.
understand, but that display device basically shows that is it working or not, right?
Yeah.
But how we can understand that if the device is not working, right? If the display device is not there, how we can know that this particular mode is not working?
Okay, so like that particular node is transmitting data to some central location. So if you are not receiving the data, then that is some problem with that particular node. So at the central locations, like you can monitor which node is sending data, which node is not sending data. So if a particular node data is missing at the central locations, you can say that that particular node has some problem. So you can go and diagnose it.
Okay, why I'm saying because these three devices are very important in the IoT environments. And I was told it to obsolete this problem particular.
So why? Because I developed the modules to monitor the soil moistures and other parameters in the fields. I implanted 5-6 sensor box in the field and I put these display devices on. So I connected the power banks, 11,000 mAh. But that power bank drained in 4 days. So then we figured out that okay, the culprits were the display devices. And we are also transferring the data to the some central location. So we remove the display devices and we are monitoring at the central location only. So central location can be plugged with the main supply. So we are checking that if the data is missing from any particular node, then that node is in the problematic situation. So we have to go and diagnose it.
Second question is, are you compatible with the Raspberry?
For Raspberry Pi, we have to change this voltage regulator, one which is supporting 300 milliampere. Raspberry Pi require for its full operations something like if you talk Raspberry Pi 5, that will require 2 to 3 ampere current. So we have to change the regulator IC and then we have to think on some other mechanism also to turn the regulator selectively so that regulator should not consume more power. So there is always a trade-off. So if you are using Raspberry Pi, then you have to think on the regulators and other things to control that. So I did a lot of mistakes in the solid state switches. We should support high output current, provided they should consume less current for the internal office. But it's very difficult to find. So somewhere to trade off.
Continuation with this one only. What I wanted to understand is that we already challenged or criticized this entire process of optimizing the power control with these standards. Because what he is saying is typically like we start with this IEEE, right? So IEEE has itself device standards. And these are some of those device standards which cannot be obsolete of.
So I have just given the name.
Yeah.
These are the culprits. You have to work on them. Like how you can you cannot fully avoid them. That's not possible. You have to work with them. Like how to avoid the voltage regulator IC. So what you can do, you can choose a battery which output is 5 volt and its discharge output terminal voltage is 4.5 volt and maximum it can go to let's say 5.5 volt. So mostly microcontroller supports this voltage range. So if you do that, you will avoid the voltage regulator IC. Okay, so you will save one component. Similarly, you can think on other components how you can avoid those things. So if you go into this, you will find that there are enough ways, but always there is some trade-off. Any other question?
Thank you, sir. I now request Professor Ashish Kumar Singhal sir to present a memento to Dr. Rohit Singh as a token of appreciation and gratitude. Thank you, Professor Singh. Now, I take the opportunity to thank our esteemed speaker, Dr. Rohit Singh, to take time and efforts to share his expertise with us. With this, we'll now move for the lunch, and after the lunch, we'll make exactly at I would request everyone to please come forward for the photo session.
Let's go palace photo session करना नहीं था और ऐसे जरा फेस से existing functionalities are very, very advanced person start.
सर एक मिनट मैं ये बोल रही थी कि थैंक्स
Session is